frame. Somebody that is at rest is specifically someone who is following the geodesic, which means that what you think of as at rest, like you're just sitting down or something, isn't in the GR sense. It's not what they call at rest, because at rest is something where you're not being acted upon by any forces, and you are just going down the geodesic in a sense.
Yeah, it's exactly that.
It's freaky.
But that it looks like the Earth is actually traveling in a circle.
No, it is traveling in a circle. Is what I'm trying to say. Is that it is traveling in a circle.
In a perfect circle? In a perfect circle?
No. I mean, it's traveling in an ellipse.
But
I mean, it's not traveling in a straight line.
So if it's traveling in ellipse, why don't you pick up acceleration? You're saying because it's nominal?
Well,
that's not what Einstein said.
So actually, yeah,
I'll pull it up. Give me a sec.
I mean, I take that back. That wasn't quite accurate. The rotation that the revolution that we have around the sun, as we're following specifically the geodesic, shouldn't have any proper acceleration. So we shouldn't be able to feel any force. And
why though? Why is that?
That's because we're on the geodesic. So
yeah,
what Einstein says, the geodesic is the shortest path around.
Bro, it's because
in this case,
the Earth is actually traveling in a straight line.
But it isn't. because okay, I wonder how
it's not traveling in a straight line. What is it traveling in?
It's traveling along the geodesic. I mean, it is traveling in an elliptical orbit. And classically, what we would say is that
suggesting that an elliptical orbit is going to be devoid of force.
In the GR sense, yes, because it is in a.
So that's a modified and a qualified answer. Still, you're just taking the piss.
Sorry.
You're just taking the piss. How can you cite threefold and no forces, and then claim something that has forces inherent? You're giving a
it has forces in the Newtonian theory.
Oh, so
we're just saying.
Wait, you think? Are you suggesting that certain theories of reality don't have interrelationships, and that you can just ignore them?
No, I mean they do have interrelationships.
When you're dealing with something that you're claiming actually happens in real life.
What I'm saying is that in GR, because we're talking about I'm hearing what you're saying. In GR,
no, I don't think you're hearing.
No, I am. You think that it's inconsistent because I'm saying that look, there are forces in Newton, but there aren't forces in GR. And the issue is that
it's got to do with the implications of your words.
I put in Google, is a geodesic in spacetime a straight line? It says a geodesic in spacetime is the generalization of a straight line due to curved geometry, representing the straightest possible path. And it says curvature versus path. While the path appears curved from an outside perspective, it is straight because it is the most natural unforced motion in the geometry defined by the gravitational field.
Paradox.
That's what I was trying to tell you, bro.
Absolute incoherence.
I mean, you can call it straight, but I mean, it won't look straight.
Yeah, depending on reference frames, bro.
No. It just won't look straight, like at all. Like locally, maybe like on the tangent path, like it'll look straight, but it just won't. It doesn't have to look straight like the way that you're thinking, like a line. It will just take the most natural motion, which is the geodesic.
Yeah, the geodesic is a straight line that the Earth is traveling in. But but depending on the reference frame, it might look like it's taking an ellipse. But it's according to the theory of relativity, it's not experiencing any acceleration because it's traveling in a straight line. Not because it's nominal, not because it's moving so slow. That's not what the relativity says.
So there is no You're right that it's not because of how slow it's moving or anything like that. Though if you do calculate that, it would be very, very tiny. It's not because of that. But once again, you're saying a straight line, and from what I can tell, you seem to be kind of distraught at the fact that it's an ellipse, but it's also a straight line, and that's like a paradox or something like that. Is that what your issue with it is?
Not even, because it's all depending on reference frames. So from one reference, it's going to look like an ellipse. From the other reference, it's going to be traveling a straight line.
So yeah, I mean, it just won't. There's no Lorentz transformation that you can do for any reference frame that will make an ellipse look like a straight line. I just want to make that clear. Dude, that's not, when they say straight line, they mean specifically a geodesic, and a great circle is a geodesic on a sphere, and that doesn't look like a straight line. If you look at it locally, it looks like you're traveling in a straight line, right? But when you actually look at the entire path, it's not a straight line, it's a circle.
Yeah, I'm not even denying that, dude. I'm just trying to explain to you your own model. It says that the reason that we don't experience acceleration, even though the Earth is traveling around the sun in elliptical orbit, according to your model, is because of curvature of space-time, because we're traveling in a straight line. And I don't know why you resist that.
I mean, if you can respect the idea that it's not an actual straight line, then sure, yeah. As long as we're agreeing on what that means, then that's fine. I think this was. I guess it seems to be more of a semantic argument.
Einstein didn't believe it was illusory. He actually believed that objects that are in a geodesic are traveling in a straight line, dude.
Okay. What do you mean by a straight line here? Are you saying that the elliptical orbit is actually a straight line?
The mass of the sun itself is causing space-time to warp, right? And the mass of the Earth is causing space-time to warp. And combined, it makes this ellipse around the sun, but it's actually traveling in a straight line, dude. I don't know. I can't comprehend it. To me, it's incoherent. But that's what you guys say.
That's not.
You don't say.
So the masses dictate the geometry of space-time. In this case, we have the mass of the sun, we have the mass of the Earth, and that will cause deformations in space-time. Where you can think about it like the classic, like you have a sheet, and then you have like a ball, going around it. The classic one. And
what value does a
those
theory have that's built upon claims?
So those obviously aren't like straight lines that the object is traveling in, but it's traveling in basically the easiest path that it can take. It's traveling along the path of least resistance in that case. And locally, we can treat it as a straight line in the sense that in Newtonian physics, an object that's moving along a straight line path at a constant velocity is not experiencing any forces. And then in GR, we would just say, well, the geodesic is the equivalent of a inertial straight line path. So we are inertial. We're inertial observers here, but that doesn't mean that the ellipse is a straight line. What that means is that locally, we can basically treat it as if we're traveling on a straight line for all intents and purposes. But naturally, like our position is going to be going around. Like those are.
How do you know that though? When Einstein said there's no preferred reference frame, there's no absolute frame of reference, dude. So either it's valid.
That has anything to
it absolutely does, dude. It absolutely does.
What do you mean? There's no preferred reference frame? Yeah, but so what? What does that have to do with it?
Instead, we don't pick up any acceleration. So which one do you think is a more plausible?
Yeah. Sorry, I'm trying to. Travis sent a thing. Yeah, the curved and elliptical orbits in 3D space in 4D space-time is a quote-unquote straight line. But again, that doesn't mean that it looks like a straight line.
Would you mind reading the top of that?
Yeah, in general relativity, planets travel in straight lines, which are called geodesics, through curved four-dimensional space-time. That's
thank you.
Yeah, sorry. But I mean, that's true, but straight lines isn't a straight line in 3 space. It's not a straight line in 3D space. This is a straight line in 4-dimensional space-time.
Just so we're clear, I don't believe this stuff, bro. Right? This is your model. I was just seeing if you agreed with it.
That's fine.
Apparently, you didn't agree with it, but now you do, right?
Agree with what? I just wanted to make sure that you didn't think it was a straight line in real life.
The geodesics are straight lines.
In 3D space, or
yeah, the geodesics are straight lines
in
space-time. Yeah, in space-time.
In space-time, not in space. Not just in space.
Yeah, in space-time. I said that. Space-time is curving around the mass.
As long as that. Okay, sure. There are things that you say, and they're not technically true, and I have to address them, and then I feel like it gets off of like any productive topic here. I mean, it's not that the space-time curvature is like curving around them specifically they just follow this path of curvature.
The reason I brought this up is it goes back to the Cavendish experiment, because at the macro scale, we're talking about orbital mechanics and the Earth moving around the sun in an asymmetrical orbit where the focal point isn't even centered. The sun's not even at the very center of that revolution, right? If the sun was at the very center and the Earth was moving around symmetrically around the sun, it would be a concentric circle, right? That's what Tycho Brahe believed in. Instead, Kepler had to come up with asymmetrical orbits that have an ellipse, and not only an ellipse, a deceleration and an acceleration during its revolution, right? But the weird thing is, we don't actually pick up on that acceleration, right, or the centrifugal forces. Now, you might say it's because it's nominal or very small. That's not what relativity states. What relativity states is that the Earth is traveling in a straight line, and because of the curvature of space-time, it's in an inertial state, it's in 0 Gs, and that's why you can't pick up on any of these forces. That's why they're known as pseudo forces. Now you can treat them like actual forces, and you can use the math, but Einstein said they were pseudo forces.
Yeah, so
that's why. So when you bring it down to the micro scale in the Cavendish experiment in the lab, can you pick up acceleration with these masses that are attracting to each other?
I mean, they're not okay. So they're not orbiting each other in the Cavendish experiment. So I mean, that's one thing. Can you pick up the acceleration? You can see them being attracted towards each other, and the acceleration that they're experiencing. They're experiencing acceleration from the Earth, and they're experiencing acceleration from each other, and they're following the geodesic path between them. So they wouldn't experience technically acceleration, but they would still move. We just need to detect that motion, and that's all it would be. But were you, if I'm not mistaken, you were also kind of you mentioned the fact that we should experience a force, but then GR says we don't experience a force, and then this and that. And I think I have a good kind of response to that, which is that the forces that we would experience in an elliptical orbit were made specifically before general relativity. Okay, that's one thing. I didn't actually mean to react like that. And what was I? Yeah. So rotational motion. When we talk about rotational motion, it's specifically talking about rotational motion that is not on a geodesic in the sense that we're thinking of here. We're talking about geodesic motion, and that is a completely different phenomenon, actually, from rotation due to some other thing. For example, if I have some like weight and on some string and I start rotating it around, that is going to experience a force. And the reason why it experiences a force is because it's not on the geodesic. It is experiencing forces from things. Okay, someone stopped miking. Who's that? I'm going to mute them. Oh, nice. So the reason why, for example, if you take some rock and you tie a piece of string to it and you rotate and you swing that around, that thing's going to be experiencing force because it's not on the geodesic. Because that thing is experiencing an external force, a force that is not specifically due to the curvature of space-time, which means that it is undergoing a force. Those elliptical orbits that you're thinking about rotational motion intuitively. You're thinking about rotational motion that is not on the geodesic, and you're thinking of what force you would experience if maybe you were going like around a carousel or some track or something, and you go around a curve and you experience that force because you're not in the geodesic motion. If you were in the geodesic motion and you had intuition for that, then it would be a lot more. It would be an easier pill to swallow, I think. It would make a little bit more sense to think that, oh, look, on this ellipse that is the geodesic in space-time, we're not actually experiencing any forces. So the reason why you'd think that you would need to experience forces there is because you're thinking of forces that are specifically caused by going against the geodesic, in a sense. You're not on that geodesic path. Hopefully that made sense.
It's a lot to accept, from us.
Yeah, you can prove it to yourself, though. Very simply, if you look at a roller coaster like the Superman ride that gets a bunch of speed, then it goes straight up, you're weightless the moment it starts decelerating upwards, comes to a stop, starts accelerating downwards, and the entire time, even though you're going through this intense deceleration, stopping, and then accelerating again, you're weightless the entire time. You don't experience any acceleration from your perspective.
Like at the peak of the roller coaster.
Yeah, only at the very peak, when for a second, in a moment in time, before you start to accelerate again, because you would, as you move up, you slow down, you pause, and then you move back down. You do experience acceleration there.
You're experiencing weightlessness the whole time. That's the whole principle.
No, you're not. No, you actually.
Oh,
what are you talking about? I've literally held a coin. I've literally held a coin in front of my face through that whole run, and it just floats in front of your face. It's the same. It's the same parabolic trajectory that the vomit comet does, where you're weightless.
Oh, that's cool. Okay, so I think we're talking about a specific roller coaster.
I know we're talking about weightlessness. But before you actually before you reach that moment of weightlessness, there is acceleration that you can pick up with an accelerometer.
Yeah. The accelerometer actually, what it actually measures, the accelerometer that they're probably used to, is it measures acceleration in addition to the geodesic. So if you were in free fall, the accelerometer wouldn't pick up on any acceleration, right?
No.
Right. It wouldn't pick up on anything. And so when you're like just standing, right, the accelerometer, well, okay, it does also have to take into account gravity. So what accelerometers are actually they're actually tuned beforehand, right? They're what's the word I'm thinking of? I forget. But basically, they have to take into account the fact that you are at quote unquote at rest. The fact that you're not in free fall, they have to take that into account. And actually, I don't know if maybe not every phone has it, but there's an app called Fifox, kind of a poor name, but it stands for like physics Fox, I guess. I don't know. And it allows you to look at all of the different tools that you have on your phone. And there are two tools. Well, there are a lot of tools, but two tools specifically. There's the accelerator with G, and there's the accelerator without G. So you can look at the accelerator with G. If you turn it on, you literally can measure the acceleration that the ground is exerting upon you to keep you from going to the center of the Earth, to keep you from going on that geodesic. And so when you're on whatever the Vomit Comet or on the Superman ride, the reason that you're experiencing weightlessness is because your trajectory is such that the seat underneath you and the ground and all of that underneath you doesn't have to stop you from going, doesn't have to accelerate you upwards to keep you from going down to the center of the Earth. And so you don't experience any weight, and that is that is a forceless frame in that sense. Your proper acceleration there is 0.
There's a
But
lot.
hopefully
There.
the ellipse,
You said
hopefully the ellipse stuff made sense.
you're talking about little g versus big G, right? When it comes to weight. What's the formula for weight?
The formula for weight is, well, I mean, it's going to be mg is the force that you, m little g is the force that you
Mass times
experience classically. Mass times the gravitational acceleration. Which, to be clear, is the acceleration that the ground needs to exert upon you. In GR, the ground needs to exert upon you to keep you from going through the center of the Earth. That's the acceleration that you'd see there. Though, well, actually, that's not quite right. That I misspoke. That's not true. The acceleration that you experience due to gravity, the acceleration g. So the acceleration g is your trajectory on the geodesic when you have Earth as your initial conditions. That's your proper acceleration. On that would leave it be 0, but your coordinate acceleration wouldn't.
We lost like most of the people, dude. I think they got bored.
Well, I'm not really.
It's late too,
so.
No, it's all good.
Yeah.
Good.
No. Nice. It is late. I've been. I mean, yeah, man. It's past my bedtime. I mean, I got shit tomorrow early in the morning. Bright and early. But it's always nice to kind of remember. These are always nice because it lets me think about things that normally you wouldn't see in textbooks, in the sense like they won't ask you a lot of the questions that you guys will ask me, and that's helpful. It allows me to better understand what I know and to see what I need to work on. I think the rotation, like the sort of like the elliptical motion and all of that, that was actually pretty helpful, at least for me. It made me really think about it. But yeah.
Oh, there's more, bro. I'm kind of tired, but I would love to continue this maybe tomorrow, if you don't mind, regarding accelerometers and weight.
Yeah, I don't really know. I can't make any promises. Yeah, tomorrow.
Whenever, yeah.
Maybe we'll see. But whenever I'm,
I haven't seen you in here.
Yeah, I'm in here once every couple months, basically. I finally got ahead on my work, so I thought it'd be a good time, but that's somewhat rare. So, but hopefully some of what I said makes sense. When you think about that elliptical motion, you're thinking specifically about just like rotational motion. It's difficult to think about it in the context of what's actually going on, which is you have two bodies that are traveling along geodesics, right? You have one body, yeah,
both,
and so, yep.
The sun has a greater geodesic that it's traveling through, right?
Yeah, it's traveling around
Through
the Milky Way. Yeah, pretty insane.
Yeah.
It's really cool to think about. I don't. Yeah, I mean, the reason why you would think that you would have that kind of acceleration, like that you would feel a force when you go around that ellipse is because uh, you're not thinking of you're not thinking of specifically free falling basically around this object. If you're free falling around it, then you don't experience any forces like that.
Well, that's what we naturally see on Earth. That's why we would expect to actually pick up on those forces, but we don't pick up on those forces.
Like what forces?
Like Newton's bucket, dude. Like just like classical mechanics.
Yeah, Newton's bucket was right. I think that actually. I think the fluid in that bucket should be following the geodesic in that. No, it's not. What is it?
The fluid itself experiences centrifugal forces, dude. It does wrap itself back into like a parabolic curve, but the fluid itself, because it's being spun, experiences centrifugal forces.
Yeah, I mean that's fine. Centrifugal forces exist. I'm not saying that they don't exist. Those definitely exist. But what I'm saying is that those centrifugal forces are within the context of something that isn't in free fall. If you took that bucket and you went, in free fall, orbiting the Earth, I don't think you would have that exact same effect. I don't think it would. Well, it wouldn't be parabolic because there wouldn't be an asymmetry in the force specifically pointing down. But
just things that are elliptical on Earth, right? Like I talked about earlier, a Formula One racetrack, dude.
Yeah, I mean, non-inertial motion, like non-inertial frames, you definitely have forces that arise from that, and you would, yeah, I guess you, yeah,
those forces disappear with relativity.
Well, they disappear specifically in the context of orbits, because that's not technically rotational motion in the same sense. Because the rotational motion that you're thinking of is rotational motion kind of outside of this idea of the geodesic, right? Even if you're traveling along the geodesic, actually, if you're rotating something, that object still traveling along that geodesic can experience a force, just not due to its motion on the geodesic. The geodesic, like the path that it's traveling around, shouldn't generate any force, but any rotation of an object in that should. It's not. I don't think it's an easy concept to grasp. I don't think anything in relativity is easy to grasp. It's hard. It's hard stuff. Wonder.
I think at this point you need to tell him about the ground accelerating upward.
Yeah, that is.
I didn't even ask him that. I was waiting for you to step in, dude. I was waiting for you to say that.
That's what I've been saying actually. Is that because your proper acceleration is non-zero, the ground is technically accelerating you upward to keep you from going through the Earth to the center, following the geodesic.
And then what they're going to
actually so insane.
Then they can't figure out why the Earth isn't expanding in all directions, and then we start realizing what acceleration really is. It's not just a change in speed; it's a change in direction. And really, what's changing is the direction, not the velocity or not the speed.
Yeah, exactly. Your direction through space-time is being changed.
Right.
Not just space, and that's one of the really interesting kind of consequences of GR.
Right.
No, I agree. It's wacky. It's very interesting.
And I think the orbits are really the mind-bending part too, because you got, if you talk about, Neil deGrasse Tyson talks about when something is the cannon, you're matching this velocity is matching the curve rate of the Earth. But you can look at it also as this, what Tor is saying is that you got a velocity that has a centrifugal force, and it's matching the weight. When the centrifugal matches the weight, then it's weightless and you're falling around it. But it doesn't. I guess you're kind of mixing up
that wouldn't be,
yeah.
Yeah, that wouldn't be why. Like, the reason why you're weightless isn't because you're moving so fast that it like pushes you off from or like it's rotating. So no, it's just specifically because you're on the geodesic. Anything on the geodesic should be weightless, shouldn't experience any force.
Right.
Like specifically because of that. Like if you're on the geodesic and nothing else is happening, you're not experiencing any force. Of course, you could be rotating on the geodesic and then you'd experience force, but not from your motion on the geodesic.
Not from the path on the geodesic. That's how I've always explained it. But then I started questioning that because you start thinking about Newton's cannon. And
I don't know about Newton's cannon. I know about his bucket, but not his cannon.
Yeah,
I don't know if I want to know about his cannon.
Maybe not. The velocity, if people kind of confuse why an object will go farther and farther as it's shot faster and faster out of a cannon. And there's really two ways of explaining it. One is right, and one is kind of misleading or incorrect. And I think you've already talked about the correct ideas, and the confusion is the centrifugal force matching its weight.
Mm-hmm.
Because it has a centripetal force pulling down, which is gravity, its weight, and then you have this velocity that's following the curve, and that's the centrifugal force that's usually mistaken, I guess, in that particular area.
Yeah. That's I've seen that a couple of times. There have been a couple of students that it's easy to get those things mixed up. At least me personally, the bins that I hold them. I have ideas in bins in my head, and the bins between those concepts are pretty close together. So I get it.
Right.
Makes sense. But yeah, I'm. Oh God. Oh, it's.
I had a question. When something's flown at the geodesic, I'm thinking about like the ISS or any kind of orbiting satellite or spacecraft, because it's falling in a geodesic and it's really just free falling. For me, bring it back a little bit. Let's say I'm in space, and I'm approaching the Earth, and then it gets captured by this. I know there's no gravity wells in Einsteinian, but they call it. You have this bending and warping of space time, and it's curving. Its direction is curving. Would the nose of the spacecraft start following, because which theoretically shouldn't change its orientation either, or would it just kind of go forward, get into this geodesic, and maybe start falling horizontally, and then maybe start going backward, and then be like a Ferris wheel, or does it actually follow the geodesic as if that's following in that direction and there's nothing? It's a straight line. That's where I get kind of wrapped up around the axles.
Yeah, if there's no force to stop it, then it will just continue on the geodesic wherever that may be. Are you thinking of like there's the Earth, and then suddenly you have some sort of gravitational field that pops up around there, or
you're in a spacecraft approaching the Earth and you're heading toward the sun, let's say. So you're facing the sun and you're getting toward the Earth, and you're just high enough to where it's not going to crash in the Earth. It's going to go into an orbit. It's at the right angle and right velocity that's going to go right into that, follow that geodesic. And would it nose down and go around the Earth, or would it kind of go toward the sun and then still be facing the sun and go around the Earth and go backward and then come up and be like a Ferris wheel?
Oh yeah. So I think in that case there shouldn't really be any torque exerted on anything there. So I think whatever orientation you have initially going into it, you're going to just preserve that throughout your orbit. But there's
tidal forces, though. Don't forget.
Yeah, they're tidal forces, but tidal forces in GR are a little tricky. I honestly, it's been a minute. I could check on my notes, but it's a little bit more complicated there. And I think if you discount tidal forces for a second, then like you shouldn't really be changing your orientation. But there is also geodetic precession. So I guess your orientation would actually change because of geodetic precession. Yeah, this is actually an effect that you wouldn't predict in Newtonian mechanics, and it was verified in 2015. There's what's called Gravity Probe B satellite that tested two predictions of general relativity, and one of them was geodetic precession, which predicts that the angular momentum of any object, basically orbiting as a satellite orbiting something, will actually drift through time, which is pretty insane. And that was one of my homework assignments like a year or two ago when I took GR. It was very fun, very very fun class.
Oh, glad I brought it up, because I haven't had anyone really address that for years now. I'm thinking about it. And usually in physics form, they don't want to talk about it, or they choose not to.
Yeah, I mean, I think that from the perspective of like, if you go up to a physicist and you start asking them questions, then I mean, if I go up to anyone and I start randomly asking them questions,
don't bother me, kid.
Like, what?
Take off. Go play with your ball somewhere else.
Yeah, if you're curious about stuff, I mean, I would say go check out like Physics Stack Exchange and ask questions on there. But actually, people on Stack Exchange are mean, and they're kind of bitches.
That's what I'm talking about.
They're kind of evil.
And I have a physics background, but it's been many years. It was just kind of some general, like, hey, just always wondered about this. Maybe the math worked out. Maybe I passed the test, but I don't really know why the cause of this. Can you explain it? Oh, I don't know. Run along, Sonny. You're an idiot. They don't want to deal with you.
Yeah, that's a classic reaction when people don't really know how to answer something.
Right.
They'll just be like, well, it's actually really complex.
Really
And I know that
complicated.
to some people who were in here, it might seem like I was doing that earlier, but I swear I'm just really bad with words. I just I'm just not great at explaining things, and that's one of the things that I'm trying to work on.
Hey, you seem like you got a good knack for it, actually. I've only listened to you for a little bit. And I'm kind of impressed with your way with the crowd here.
I appreciate that. I try to. I really love physics, so and anytime any discussion in physics is brought up, it's hard for me to kind of feel negative about it. It's just really cool to me. So yeah, I'm trying to find anything with angular momentum or like tidal forces in here, and I mean,
so that's why you have these orbiting satellites and things that have to actually impart some type of rotational angle or force so that it can actually kind of keep exact pace with your angular velocity of its orbit.
Yeah. And I mean, there's also, you have to, like, you may have heard, like, the ISS actually drops down, like in altitude, but that's actually completely unrelated because that just has to do with your drag from, the upper, like, ionosphere.
And they have enough power sources to actually eject mass out of these nozzles to be able to get it back up into the proper orbit constantly. I mean, over years.
I think they'll send satellites up they won't send satellites up, but they'll send shit up just to like basically course correct it like every couple of months, or maybe I'm just imagining that, but I think that's what it is.
Right.
I don't think they necessarily like, well, maybe they do. They probably do have like minor course correction stuff, but I haven't really looked into it. So I've gravitational, I have waves, I have Kerr black holes. Where I actually do want to find the tidal forces bit. There's stress energy tensor, but that's not.
Are the tidal forces a type of tensor force?
Tidal force. So everything in GR is a tensor. Well, actually, that's not true, but almost everything. A lot of things are. So I'm maybe not the Riemann tensor. The stress energy tensor. I don't think. I mean, I think that probably encapsulates some part of the tidal forces, but I honestly just don't remember, and that shows that I didn't really pick up on everything, and that's why conversations like these are helpful because then I can remember things.
Yeah, well,
I should
we need to
just
go
look at
back to
this.
some homework. We need to go study up and come back with all these answers. Okay, next time.
Yeah, you're right. This is like I go here and try to figure that. Yeah.
Oh no, that's a great forum to actually get all these hard questions and things I probably haven't thought about, or for me anyway, in many years. And they have some pretty cool discussion. Even they challenge you on everything. Say, nah.
Oh yeah.
But I'm being a little overly critical.
Yeah, no, it's fun.
What's your specialty? What do you do now for your work or your studies?
So I'm currently doing research in conformal field theory, which isn't. I mean, its ultimate goal is to do stuff in quantum gravity, but
Wow.
I need at least maybe 5 or 6 years before I'll have like the actual preparation to be able to contribute to the field in a big way. Right now, like and you can't go into physics without some humility because holy fuck, dude, like you could literally study math and physics for 10 years and then like half the people in the theory department are just like, yeah, you're a fucking idiot. Well, they won't say that. You'll just feel like an idiot. Every time I talk to my advisor, man, it's like this guy is so fucking smart. I'm genuinely retarded, like compared to this guy. It is insane. There's some really, really smart people up there, and you're surprised at how little they've done. I mean, this guy's done a lot, but like people, really, really smart people, and it seems like, oh man, like I haven't heard like crazy stuff from you, and it's like imagine the people who have done all of those things, how smart they would have been. And anyway, like
people that would need you to introduce to come on here and have a chat with us, dude. Like, can you get him to come on sometime?
Oh, definitely not. He's way too busy, and also I doubt he would be into it. He's a very particular type of person. I'm 99% sure he has autism. Though I'm also autistic, so I don't think it really. I don't think it's that important, but I don't think this would interest him. And if it doesn't interest him, then I doubt he'd participate. Which is unfortunate, but you know, I'm the second best thing. Jeez.
Can I ask you a trivia question? Like, why do you think the moon is the distance it is away from the Earth?
That it is right now.
Like, is it the sweet spot between the moon, the Earth and the sun? Is that why the moon is in its orbit around the Earth? Because of give us some examples, some reasons.
Yeah, so I mean, the reason that the moon is the distance that it is right now probably has to do with the way that the prevailing hypothesis is that some planetoid basically impacted Earth in like the first couple billion years, maybe like 1.5 billion years of the Earth's formation, and what happened was it took off a chunk of the Earth, and all of that debris basically accumulated into the moon, and it struck the Earth at such an angle that it all went out in such a trajectory that it wouldn't just blast off into space, and it wouldn't all fall back to Earth, but instead it would have this nice orbit, which might seem like it's like a crazy coincidence, but I think they're like a pretty large span of initial conditions that could get you that. But the reason why it's where it is right now has to do with specifically the angle and the mass of the body that hit us initially, and everything else from there is just physics. It just goes about the way that it does.
That's all speculation.
Yeah,
I mean, just come back and join up together again with the Earth, which is a bigger mass.
Because of the initial angular momentum that was imparted on it by this body that was coming in. So it had enough angular momentum and velocity to basically miss the Earth instead of falling back down. So it had enough velocity so that it wouldn't fall back down. That's how things get in orbit in the first place. They have enough velocity that they don't fall back down. Hope that makes sense.
As long as you're happy with that.
Yeah, I'm still looking for the tidal forces. I think I might have actually found it. Geodesic deviation. I don't know. My notes. I'm just like remembering how bad my note taking was, man. This is awful. I'm glad I switched over to just typesetting. It's way fucking better. Okay, maybe it's further down. The last resort is like my instructor literally just had notes. Like he just had typed notes, but I can't access those from where I'm looking right now. So
you physically till around 22. Then I fully developed my athleticism. Before that, dude, I mean, seeing the gladiator shit, like I don't think I would have been able to beat you physically.
I just didn't know what your comment was. It was kind of like, well, really, this guy's pretty full of himself. Like, at least you could say, hey, you know what, I would have given you a fight back then, but now you're like, no way, you're like 15. I would have been like, I would have walked all over you like you were a little kid. That's how I kind of took it. Mentally, physically, you're
talking about mentally. Yeah.
No, you're sharp.
I was like basically like your level of mentality at 15, and then since then I've just been like 007 compared to you.
Really? Oh, okay. So we're talking about mental boxing ring.
Yeah, in the mental boxing ring, I'm like a black ops, like special level assassin compared to you.
Whether this is true.
We got MackingCheese right now. We got MackingCheese right now.
Xanax, you know whether this is true, you now have to decipher: has he been trolling you, or is he being real? Because
I think he's being
real. If he is transcendent above you, or if you or not,
he's being real.
Better hope you don't run into him on the street.
He's the mentalist. Oh, right now, yeah, I sold like a paper, like a house of cards.
If it was me versus Zanuck, it would be a true battle of the wits on the street over here.
So there's some sharp people here. I mean, Mac, these guys they've done their homework. They've got all the nuance. I mean, they've done the high level, like the cliff notes. Every physics book you've ever read, they've got the cliff notes in their back pocket memorized. It's actually pretty interesting.
Yeah, this guy's a great addition. I don't know where he came from, but cheers.
I mean, you got a physics guy. He's fresh off the freaking mat.
What's holding you back from the knowing the Earth is in a sphere? With all this interest in physics, wouldn't that be the most interesting to know the actual physics of the realm directly with the Earth?
What's holding me back from knowing the Earth is a sphere?
No, that is planar and stationary.
Oh. Well, there are definitely a couple of things that kind of irk me. One of them is specifically the different rotations of the stars in the different hemispheres. I don't think that's very well explainable without some ad hoc kind of physically unphysical, unjustifiable assumptions.
Well, have you ever?
What I've heard.
Have you ever taken like a paddle and you drag it through water and it creates a clockwise and a counterclockwise rotation?
Yes.
That's like just basic vortex like that. It also happens with air. It also happens with
yes, fluid dynamics. Yep.
Yeah, fluid dynamics. I was gonna post this. I'm posting this. It's like an owl. It's like a slow motion of a owl, and you see the two rotations. And that happens in water. Happens. So whatever the stars are, they just seem to be doing something that is like universal in nature. This vortex pattern. So whatever that means, or however it all works with the ground and the true map and all that. Either way, also an electric field, electromagnetic field, and electric fields. You're probably familiar with that as well. That those actually make the field lines have the two rotations.
Not all fields have that. It's very specific fields that'll
like
have
this
that
here,
sort
like
of thing.
Well, this shows a ferrocell and then an electric field circuit. Also has that pattern.
Yeah.
So whatever the sky is, it seems to match this, and this seems to be like present throughout all of nature.
Yeah, that's electric dipole, magnetic dipole. Yeah, those. I mean, certainly they look the same, but there's no like physical motivation for why. And these are things that are rotating. These are, like the rotation of them would have to be motivated by something, not just kind of saying, look, all of these other things also do this. The physical motivation for the globe model is very straightforward. It just has to do with the spherical geometry. But I don't see an actual explanation in that. I do agree that there are vortices and that rotate counterclockwise and clockwise in real life, but that's because you have a stimulus and a fluid, and now you have to assume that that everything above is a fluid, and that you have these things that are rotating, but it also has to be a perfect fluid, otherwise they would slow down. And where's this rotation coming from?
Superfluid plasma, perhaps.
No, those are different.
A superfluid has very little friction, so helium-3 and other materials as well could be possibly related. But I'm just saying, you were saying, and I heard you say this earlier, like a sticking point being the two rotations. And I do hear what you're saying in terms of like how does the map work and how does the whole realm work on a plane with two rotations. And I do hear you that it does fit, like it is a celestial sphere, so it does have the two rotations and then the straight line at the equator, which basically makes the spherical coordinates. Because like if you see in the chat what I'm posting right now, it shows like the geometries. You have the spherical coordinates, and then on the bottom you have like
stereographic projection.
The azimuthal, and on the vertical you have the stereographic, exactly. So but that's a flat thing on the vertical there, obviously, but it's stereographic projections of spherical coordinates. Now, if that was the ceiling of this realm, you would get the two rotations, the straight line at the equator, and the two rotations above a plane. It is spherical coordinates, stereographic projection, but doesn't mean that it actually is a sphere, in that sense, because the way you can project it stereographically like that, it can just be the coordinates spherically, but not actually be a sphere that surrounds a sphere globe.
I don't know how much of that I exactly followed in terms of exactly what you're trying to say, but it seems like on a flat Earth, when I look up, right, in the northern hemisphere, I see something rotating in one direction, but optically, if this is a dome or something that's strictly above the flat Earth, then I should be able to look somewhere else and then see it rotating in the other direction. There should be no place that I can't look and see constellations in this sense. Does that make sense? It all has to be visible because of the way that line of sight works, the way that optics work. That doesn't seem to be the case. Like I can't see the southern constellations from the northern hemisphere, or vice versa.
Okay, well, I would say for that, like an analogy, if you had like a huge, like a Costco or like a Walmart or just some huge warehouse, Home Depot, whichever of your choice, and it was like the size of the United States, and it went all the way, and somebody was in like, New York, and someone else is in Seattle, Washington, or just take like New York to LA, something like that. And if you had like a light in the ceiling that was like 50 feet up in the air, and then you took that light and it was above the guy in New York, and then you took it all the way over to LA, like you're not going to see that light anymore. The visibility is just not even, there's so many reasons as to why you're not going to see it, but a guy with a light, I'm saying on a planar Earth, like not a globe, like on an actual flat plane, as it were, just because you only have a limit of how far you can see on the ground, and then the rest is sky. So usually on the ground you can see really only a few miles. I mean, the world record photography is like 300 miles. Like that's the longest apparently that any human's gotten. Like in that sense, so 300. But even 300 is nothing compared to the thousands of miles. So and sometimes you can only see 5 miles, 3 miles, 10 miles, etc. And that's of how far you can see on the ground, and then the rest is going to be sky. So you're never going to be able to see like 3,000 miles of ground. Unless maybe if you're at some extremely high altitude and you're seeing at a different angle. But if you're down on the earth, even if you're at a mountain, I mean, the world record photography is 300. But anyway, so I mean, there's going to be a limit of what you can see. And like I said, the idea of if there was a light above the person in New York and then a light above the person in LA, that light is just going to set, to that person in New York and no longer be visible once it gets that far away. So I just think the stars work a similar way. It seems like we see in about a 6,000 mile radius circle. And that's like what we see of the sky. And then the ground, we usually see much less of that, much closer, like sometimes only a few miles. But the sky layer seems to be, because that's when things seem to set. So it would just mean that on a plane, we just have that, let's just say for the sake of discussion, the 6,210 mile, which is the distance from the North Pole to the equator. That's when Polaris will set. So if that's when things start setting, 6,210 miles, then we see, roughly 12,400 mile rate, diameter, 6,200 mile, roughly radius circle. And then everything else we won't be able to see. So I think on a plane, that's what explains the fact that we would only see like a portion of one of the two rotations. If you're at the equator, you can see both. You can see half of both rotation if you're at the equator. But if you're in the north, you might see none of the southern. And if you're in the south, you may see none of the northern if you're far enough away. Just like they get the 24-hour sun and then 24-hour darkness respectively as well.
Yeah. So I hear what you're saying, and I mean, in principle, that certainly. I mean, I think it explains a lot of it, but I mean, the inverse square law for intensity decay for light is not. We've measured. We know how the intensity of light decays as a function of distance, so we know how far we can see, and we can calculate these things, and so we can see very, very far, assuming that things aren't occluding our vision. So the reason why long distance photography would be, over 300 miles is likely just because you got to look through a shit ton of atmosphere. But when you're looking up at kind of an angle, you wouldn't be looking through as much atmosphere, unless of course you assume that the atmosphere goes up through all of that. But then maybe you would see that. Maybe you would notice that, and you probably wouldn't see the moon either. And the fact that we can see those leads me to believe that light, I mean, at least our vision and light don't necessarily work that way. Like we don't have the reason why you wouldn't see the light bulb, from LA in New York is because you just can't you can't resolve that. Your eyes optically, you just don't have enough precision in your instrument, as your eyes, your optical instrument, to detect that. That's the reason. It's not because the intensity is too low. It's that your eyes aren't precise enough to pick it up. And also,
for that, I wasn't even. Just a quick interjection for that. I wasn't really even referring to the potency of the light. It could be the brightest light in the world. I wasn't even necessarily referring to that. I was just referring to the fact that it would set. Because if you're in New York and your horizon is 3 miles away, and that object is up in the sky, but I mean, it's not like I guess light years idea kind of in the sky, meaning it's at some limited range. So I was just referring to it in that sense. Like you're not going to see it for that reason. I wasn't really referring to the luminosity, but
okay.
If you want to keep going though, I was just trying. I guess I was just making a quick interjection there. Go ahead.
No, that makes sense. That makes sense. Yeah. I also with the setting, when something goes far away from you, it just approaches the right the convergence point, which would be the horizon. It can't set beneath the horizon. That's I think that's pretty standard in terms of perspective and optics. So that like things setting below the horizon, those pictures with like the sun where it's like halfway covered by the horizon and stuff. And I think I've heard people talking about refraction and things like that, but I feel like it happens too often and in too many situations where refraction that major wouldn't even be reasonable. That it's like, how is the sun actually going under? And not only that, but it's going under and it's not shrinking either. It's staying the same size, right? You'd expect something as it moves further away to become smaller, right? It's not becoming smaller. It's staying the same size and it's going down. And I've made sure of that. I've made sure that it's not getting smaller. I've seen many videos where people, don't adjust their exposure correctly, and then they adjust it, and then it looks like it gets smaller. And those I think are just a little silly. But I really don't know how to reconcile that, right? We see something not moving how it should, which, you know, if it's moving away from us, we would expect it to become smaller and then kind of approach the horizon, but never like set underneath it. While you know, we don't see that. We see stuff go down. We see the moon set underneath the horizon, right?
Well, I would say everything converges at the meeting place of the ground and the sky optically from where you're at, and there's attenuation and all kinds of environmental factors that are going to make the ground layer be much closer than the sky layer, and so yeah, things will set. In terms of the size change of the sun, I hear you on that. One thing is that with collimated lenses, you can actually replicate on a small scale an object not changing angular size with distance change. So collimated lenses can do that, and I have a GIF I could show if you want to see it. But basically, so like if you put a collimated lens either in front of a light and then you move that whole thing back and forward, it will not change angular size to the viewer. Or if you shine a light through a collimated lens, you can shine it onto like a sheet of paper and then you move the paper forward and back and it doesn't change angular size with the distance change. Both scenarios can be replicated. Now that would imply that like there would have to be some kind of collimated lens nature to the sky, which is, you know, a potential claim if someone were to claim that. But nonetheless, like it would have to incorporate something, because if what I'm saying is if you can replicate it on the ground level, then there would have to be something like that in the sky. So I'm not saying a physical lens, like necessarily made of some kind of glass that somebody put there, but I mean, the nature of it would have to function like that potentially. But I'm just saying it can be replicated. So that's just one possible thing. I mean, if the ground doesn't have curvature, and if the ground doesn't have curvature, and if it's not in motion, then the sky just is what it is, and how it's working is pretty wild. But I'm just saying, you know, how would we ever truly know? Maybe after we die. But I mean, the fact that you can replicate the no angular size change with collimated lenses, I just think it just shows that it's possible and that the sky could have that nature to it. And if it did, that would solve that issue. Because I hear you, yeah, things will shrink in angular size due to distance change. You know, I do agree, and that doesn't really fit. Like the idea that the sun is like a ball above a flat Earth, like that doesn't really work. Yeah, if it's like some kind of physical ball that's only a few thousand miles up or something, that because it would change angular size. Even though there are a lot of shots where it does look like it's fading, and depending on the conditions, it can actually shrink down to a little dot. But I do hear you. There's a lot of sunsets that are like very dramatic, like the huge circle of the sun, and it's like cutting off dramatically with the horizon and all that.
Yeah, I'm thinking of like the Lion King, you know what I'm talking about, like that specific fucking scene. I'm like, oh yeah, that's some really dramatic stuff. But I mean, yeah, when it comes to that kind of stuff, it's like you could, I mean, surely you could be like, well, you know, it could be this very specific process, or it could be a specific process that cancels things out in such a way that, you know, everything looks like it should be, you know, setting, but it's actually moving away this way, or it's actually, you know, everything looks like it should be doing this, but actually it's doing that. And then at that point, I just think I mean, it just feels like, no, you're kind of making things up at that point. Not to say that that's where you guys are, but just saying that like I don't want you guys to come off that way, because that's like I think that's uninteresting. I think that's like playing pretend. And I think that these things should really be rooted in kind of reasonable physical principles, because that's what we have. That's what we have. We have physics. That's what tells us. That's how we can really study the natural world, regardless of, I guess, whether you think physics is being done correctly. I guess I'm sure there are some people in here who don't think that physics is being done correctly. To which I would encourage them to actually study physics, because it is like really study it, because it's hard, but very rewarding. You get a very nice grasp on how things should work. Physics is really cool, but hard, but really hard. Yeah, take it from me.
Okay, so wait, what was the thing you were saying about? I kind of missed part of what you were saying. Which part you were saying was just you don't recommend that it's made up or something? What was that referring to? Sorry, I might have missed part of what you said.
No, it's basically this idea that, you know, it's like you're patching up your hypothesis or your theory, like the thing that people.
No, I'm speculating. I'm speculating. Like,
yeah,
the ground is just the ground. Like, whether it has curvature or motion is its own thing. But we're talking about, you just mentioned the thing about the angular size change, and then we're talking about things setting and all of that, which go together, because obviously, like the way the sun sets, you know, and which a lot of times it is very dramatic and a huge, you know, circle, and even sometimes looks larger, like it looks magnified, and so on. Even though the claim is like with a solar filter, it'll still look the same angular size, but the view of it can be. There's also the moon illusion, they call it, where the moon looks huge on the horizon. But anyway, we're just talking about all of that. And what I'm saying is that you can replicate something not changing angular size with distance change with collimated lenses. Therefore, it's possible in speculation that the sky functions in some way has that effect to it, that collimated lens effect. And if it did, then that would potentially be an explanation as to why everything occurs the way that it does in terms of not changing the angular size when it comes to the sun and the moon like that. So is that what you were saying? You think is just what would be the problem with speculating and showing that it is able to be replicated as a refutation for somebody saying, oh, well, the sun doesn't change angular size, therefore Earth must be a sphere? Because now you're using that to assume something about the sky when I'm showing you it can be done with collimated lenses, but then you're using that thing about the sky to say, oh, there's no way the Earth could be a certain shape.
Yeah. So, well, I think it's good that you're being honest about it as speculation rather than necessarily an assertion. Because I think that I think what I would say to not do, just in my opinion, is to start asserting that, like, then this is how it is. Like you're being speculative, and speculation is always good because that can give birth to new ideas. And I think I think it's a good move.
Well, I hear you. I mean, well, the thing is, I don't think any human can actually access the sky field. I don't think they're going to space, and I don't think that, what they call space. I think there's a limit that they reach to where even if they launch up the biggest rockets or whatever. So, I mean, I think the sky has always been a mystery to humans since the dawn of time. Now, if you're like out of your body or you're having some kind of spiritual experience, perhaps you could know more on that. But I'm saying in terms of like as a human, I think it's in terms of our physical senses, and if we're talking about like science and provability and tangibility and all of that, I don't think any human has the ability. We can point things at it. You can shoot things at it, like when they do radars and things, you can, but I don't think you can ever go up there to like see what it is or get a sample as a human. Like maybe, like I said, out of your body or, metaphysically or spiritually in some other way, or maybe after we die kind of thing, but in a physical body. So, I mean, that's why all we can really do is observe the sky. We can point spectroscopy machines at it, spectrometers, etc. You can view it, observe it, obviously all the things, but I don't think any human can go tangibly access it. So, how it's actually functioning, I don't think anyone can know unless you're like out of your body. So I think really all of it's a speculation when it comes to somebody trying to claim physically, tangibly what it is, in my view, when it goes to that. I just think it's a mystery for all beings, all humans, physically.
Yeah, I can definitely see where you're coming from because like shit is mysterious. I agree. I'm very anti the sentiment of kind of mysteriousness and therefore it's completely inaccessible. I think it's at least worth trying. That's what I'm not going to sit down and take it and just be like, well, we'll never understand this. I want to really try to understand it. And I get that, like, everyone comes from different backgrounds. So motivation and all of that aside, me personally, I'm really big on, when I don't understand something, I really dig deep and I try to understand that thing. And I've been trying to understand, space and physics and math for the better part of, God, like 90% of my life, I'd like to think. And I don't understand it, and like not fully. And so, God damn it, I'm gonna keep working at it. I'm gonna keep working. And I think that's, to me, that's part of like that's part of my identity that I'll probably never do away with. It's just so natural to me to do that. And
No, but that's going to be a tough one with the sky, though. That's a tall order. If you're going to be like, I physically want to like go, tangibly access like what the sky is, how it works, all the energies involved, the material. Now, I know like in astrophysics and in mainstream science, of course, they have their model of the globe and that they can go out there. So I guess from that view, there's the idea, maybe we would someday be able to go out there and actually tangibly, and they already claim they're doing that to some extent. So I hear you on that, but I'm just saying if somebody is like their main goal is to want to know like fully what the sky is, like I think you'd have to go spiritual on that, like have it, out of body type experiences or like powerful mystical spiritual experiences to transcend to that level. Because I don't think in a physical body it's accessible. Like I don't think that whatever this realm is, whether you see it as a creator or not, or a creation or however you see it, I don't think the sky is like an accessible realm for the physical human, for a physical body. Spiritually, yeah, that's a whole nother thing, but as a physically. So that's the thing. That's like your one thing that you really want to know, like that, without having some psychic or some other kind of abilities or something like that, or just spiritual experiences. I'm just saying it's a tall order to want to know that one. But other things like physics and on the earth and stuff, obviously, you see what I'm saying. It's just it's like a tall order. Like I want to know everything about the sky, how the actual sky works. It's like such a deep thing.
Yeah, I guess I just don't see it as really that much. I think like the principles that we have about physics on Earth could also apply to the sky and to everything else. And that's an assumption. That's an assumption that I'm making. It's an assumption that all physics makes. That's that physics acts the same in every patch of the universe. And the reason why we do that is so we don't go fucking insane. because what if physics was different over there? You know, that could explain all of this stuff, and then we would never get anything useful done. And
but then you get the dark matter problem, ironically. So then you get that. So because physics doesn't work everywhere the same. But I hear you. I mean, ideally, but I think they've tried that. It doesn't seem to. There's no like one size fits all so far.
Yeah, not so far, I guess. Along the lines of very kind of modern, what would you call cutting edge kind of problems in physics. But it's really like it works for almost everything, like everything except for like a couple of cases. Like it works quite well, in the sense that like the amount of shit that you can do with physics, like it is ridiculous. It is genuinely insane. Like with some of the models that we have, it is nuts. And I find that really interesting because this thing can, to ridiculously high precision, predict things that you would never dream of predicting. So, in at least the respect that its usefulness is undeniable. And I think that we basically, based on what we understand and the experiments that we do on Earth, we can apply some of that to the sky and understand it. But then again, everyone's entitled to their opinion. I'm honestly not super interested in if there are people who are willing to have their minds changed. I'm here for it, but ultimately, what I'm here to do is discuss reality in the sense that is reasonable, which is that we can understand things, and we should try. We should at least try to understand things, even if it is a tall order. I think it's worth at least trying, and that way we can get to some actual the closest understanding of reality that we can possibly get to, because we'll never fully understand reality. We want to get as close as we can.
Yeah, no, I got you. I think just originally the whole combo, just in terms of, because I mean, obviously some of those points are like debate points and going into that kind of mode of the different points on those. But just overall, I guess I was asking just because with all of your interests, and you would have your own journey with obviously thinking what the Earth is and all the different ideas of it. But it's just like what percentage in your mind is the Earth planar and stationary? Like that it has no curvature, that it's of a planar nature. Obviously there's elevation changes, and then it's not in motion. Is it like a fraction of a percent?
Like what's like the what probability would I assign to it? Like what's the chance that it actually is like this, or as opposed to that?
Exactly.
I mean, I would say pretty close to zero. As close as you want. Take epsilon greater than zero. It's specifically because unless I'm convinced on something, I just generally don't believe it. That's how it is. That it's actually difficult for me to learn concepts a lot of the time because I need to basically learn, like really understand it. And I think that my standards for like buying things, like really believing things are quite high. So if there's like a little bit of an outlier in, well, I wouldn't go that far, but I would say like if there are some inconsistencies and I just can't imagine it being true. That's actually why I'm agnostic, is because I just like I actually, you know what, I don't want to bring religion into this. It was just like I'm just unconvinced of a lot of things, and in physics, I go into it with the mindset of being unconvinced. They're like, "This is how this works." Here's the energy mass relation. I'm like, I don't buy that. Why? And then I have to figure it out. I have to figure out why. And that's fun for me. I enjoy doing that, which is why I enjoy doing this, because I get to better understand what you guys think, and I get to better understand what I think too. I think a lot of people don't realize how little they actually know about themselves, about what they know. And I think a great way to explore that is discussion. Just fucking talk about it.
Yeah, no, I got you. So, I mean, if your interest, obviously you're in the discussion, so you must, even though you may think it's only a small percentage that the Earth actually could be planar and stationary, but at the same time, I mean, we talk about a lot of topics you're probably interested in too, so it would make sense there. And but I mean, what I'm asking, I guess what I want to ask is like in your work in the world in the future, like from the perspective that the Earth is planar and stationary, wouldn't you want to be like on the cutting edge of that?
On the cutting edge of like
well, like the whole unified field theory and all the issues in cosmology, like what is the issue? And I know that you're saying it's a small fraction of a percent that the Earth isn't actually a sphere. It's not in motion. The heliocentric model is not true, etc. I mean, we know our ancient ancestors all had a planar stationary type Earth, but not to get into that whole discussion. So I mean, the globe has been this. So I guess I'm just saying,
like, very the Greeks were uniquely not into that. Actually, wait, hold on. There's specifically one thing that I wanna kind of pick your brain on, because I recently watched a video from 3 Blue 1 Brown about the cosmological distance ladder, and it turns out that the ancients, very very good video. The ancients actually what you can do is you can basically calculate the distance to Venus and consequently the sun and figure out all of the distances to all the planets based on the phase. Well, okay, the Venus was one thing. Sorry, the distance to the moon is or hold on, I might be confused. No, is you can use the moon's phase, the angle that the sun kind of would shine on it to get an approximate distance to the sun. And it was it was a very interesting calculation. And basically what you would do is you would take a look at what the angle that the light from the sun makes on. You have to assume that the sun is shining light on the moon, of course. If you assume that, then you'd basically be able to figure out how far away the sun is based on the angle that that light makes with the moon, since you already know, we're assuming the distance between the moon and the earth from lunar eclipses. I wonder how you can kind of think of like lunar eclipses for one are a thing, and also the fact that like the angle that the light from the sun makes on the moon is sometimes like that angle would be impossible unless the sun was very very small and local, in which case its motion would be a lot more apparent and it would be changing size, like it would be on the scale of the moon and things like that, or which it'd be a little bit difficult to do, or it would have to be super 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 far away. I guess what I'm trying to ask here is how you would deal specifically with the lunar eclipse stuff, because we see the moon is covered by the shadow of something, we'll say, and we do see that, and we can see that the shadow is always circular and that it's always a specific size with respect to the moon. That's, to me, I think that's pretty damning. Lunar eclipses are actually something that I haven't thought of much in terms of the flat Earth, but lunar eclipses are pretty damning evidence in my head that the Earth is spherical and that the moon is a physical object too.
They're not going to like that possible selenium eclipse.
Well, no, I was going to say I understand what he's saying. A lot of these points. I mean, one thing with the cosmic ladder thing and the angle with the sun and the moon and so on, that has to assume the Earth is a sphere. Now they claim like sticks in the ground and the other components of why but that involves assumptions as well. But to have that calculation of the angles, that incorporates the R value, essentially the radius, which then implies that if you put it on a spherical model, then the sun would have to be at that distance related to, if you conceive it that way. But these are like coordinates in the actual, like these celestial bodies are coordinates, and they can be interpreted in different frameworks, in different models. I think there's a certain equivalence, like kinematically, to some of these components. So, because if you have a sun and the moon that are whatever they are, like, I'm not saying that they're balls, but whatever, I mean, there's some kind of object. So whatever that is, I mean, whether it's a holographic plasma material or whether it's, physical at all, but whatever it is, they are in their positions. And the moon does go through its phases in relation to the position that it's in relation to the sun. So that is for sure as well. Like the position of the moon and sun in their 360 degree, positions definitely correlate. But I think it's also an assumption to think that it's the sun's light, like the physical light bouncing off the moon. But it's like if you see it through that lens, you can then apply the math and extrapolate it in that 3D physical, like balls kind of concept of the solar system. But I would say that that's just one way to interpret it. And that's why, like, somebody was kind of joking, saying that like the whole heliocentric globe model, like the whole thing is just like a philosophy about what the sky is, which is kind of funny because actually a lot of the globe is built on the sky in terms of what the sky is. It's just funny, one time someone said that, like, the whole thing is just like a very complex philosophy of what the sky is, like heliocentrism. But is it actually true? Is it actually what's in the physics? So anyways, you mentioned the cosmic distance ladder, and that's only involved if you make the Earth a sphere, make the sun. because you can have the sky be whatever it is, and if you say, you know what, I want to actually think of this as spheres out in a 3D environment, you can extrapolate the geometries, and I think that's what they've done. But I do hear you on some of your points. I mean, there's a lot of nuance to get into that with eclipses. I mean, I think there's another body up there, very likely, that's involved with eclipses, and it has to do with polarization and like the lunar nodes, the north node and the south node, which the globe does admit that those exist, but they just claim that those are the point at which the ecliptic and the moon's orbit intersects is what those nodes are. But I think those nodes are actually celestial bodies, essentially, or they're celestial points in the actual heavens, which is what the ancients thought as well. So when eclipses happen, I don't think that's the curve of the ground you're seeing. I think that's the polarized lens effect of eclipses.
Well, Gio, you're referring to Eratosthenes when I think he was actually referring to Aristarchus. We're talking about a true half-lit or quarter-lit moon directly from the surface, regardless of what the surface of the Earth looks like. Just talking about distances for the Earth to the moon to the sun. And we have like an 86 point or 89.6 degree angle between you, the moon, and the sun, and it's half lit, knowing that the light is coming from the sun, lighting up half of that moon that you can see. It looks like a half moon to someone on the observer on the ground. That angle means that the sun has to be 300 times farther away. Then it's simple trigonometry to figure out how far the moon is away from the Earth, regardless of its surface quality. It might be a little variance if it's round or flat, but not very much. So that's what I think he was referring to. That's what MackingCheese.
No, I was referring to that as well. No, I mean, I might have mentioned Eratosthenes somewhere in there, but no, we were talking about, he was mentioning that in relation to the cosmic ladder concept.
It doesn't technically have much to do with the So the reason why you can actually do that is because the ancients also knew the distance to the moon, which they calculated primarily from lunar eclipses, assuming that the shadow that you see is the Earth's shadow, which I think is a perfectly reasonable assumption if we assume that light behaves how it honestly does. And you would see, on one side, the sun is in this model, the sun is on one side of the Earth. The Earth is, blocking the path of the rays, and then the moon is kind of crossing into that path. And that is by far the simplest explanation that you could have for it. And Occam's rays are just completely takes you away from there. I think it's I think it's so like simple, and so I wouldn't say obviously true because nothing is technically obvious, but compared to what you might have to assume, like on a flat Earth, that just seems like it would be so much more difficult to make sense of, right?
Can I flip the script? Hold on, let me get in there. Hold on, let me get in. Can I flip the script? What about back, let's say in ancient times, for eons of time, hundreds, thousands of years, however long, these peoples thought that the eclipses are caused by a cyclical nature of the lunar nodes, which, like in the Vedics, they called them Rahu and Ketu. They had names for them, these celestial bodies, Rahu and Ketu, the north node and the south node, and then the sun and the moon. And imagine that for, just hundreds, thousands of years, however long, they had that view that it's that it has to do with these other celestial bodies that are usually not visible. You could call them dark bodies maybe, but they're non-visible. But when they intersect with the sun and the moon, you get these eclipse effects. New moon, full moon, lunar eclipse, solar eclipse, respectively. And so I'm saying, what would you say to them if they for a very long time had that viewpoint, and they even had names for them, and when the eclipses happen, they know how, because astrologically we know, and astronomically we know the positions of those lunar nodes. They're always in retrograde, and it takes about 19 years for them to do an entire rotation. So they're always in retrograde, and it's a 19-year cycle. So whenever that sun and moon line up with it, new moon or full moon, and so they know where these are in the sky, and therefore when this eclipse happens, they think of it as those celestial bodies lining up. Now, if you went to them, that's what I was trying to say, flip the script. If you went to them back then and said, well, actually, we're on a huge ball, and we're spinning, and then the sun is out in a massive vacuum of light years, and the sun is 93 million miles, and it's this massive sphere, etc. Wouldn't you think they would say, oh my gosh, you're going really out on a limb to explain something that we already have an understanding of? Can you see it flip side? Whereas you're saying the flat Earth explanation seems so out there, but back then they would say the globe Earth explanation. They think we're on a ball and then we're all stuck to a ball and going at thousands of miles an hour, and all of that.
Yeah,
you know what I'm saying?
No, definitely. I see what you're saying. I guess to me it doesn't really matter what they would think because they had to, assume these extra kind of more complicated things that they didn't truly understand them. They just said, "Oh, this thing explains it." But I mean, the mechanism for by which that happened is, first of all, I don't know exactly what you're referencing. So maybe they did have like a physical mechanism for it. But what I'm assuming is that they basically just named the process of these things happening, and then they identified it with something, and then probably assumed some sort of causality between them. I could totally be getting that wrong, but I mean, it's still much more simple to just be like, it's the shadow. it's a shadow. It's just getting in the way. It's a shadow. It looks like a shadow. It is a shadow. That's just so much more simple that I understand how going from, all of my shit was basically been like, oh, look, everything is explained by these kind of tales and folklore that we have, or these concepts that we've come up with. But their concept of explanation, right? Many of them thought, that lightning and thunder was created by a deity being mad at them, or something like that. So explanations are these were stories that were made to explain things that they didn't truly understand. And I think that the shadow, it really isn't that huge of a leap. You're assuming one thing and then everything follows from that. And I think that kind of simplifying assumption is really really powerful. But I definitely get how kind of jarring that would be for an ancient culture to kind of be told that, especially if I'm like dressed in a fucking like a hoodie and I got like a beanie on and got fucking slacks on. They're like, what the hell is this guy wearing? And it'd be a whole mess. I agree.
Right. No, I got you. That's funny, man. No, I got you though. Yeah, I mean, yeah, if you showed up in a back alley, like, hey man, that eclipse thing, man, we're actually on a big ball. No, but I hear you, dude. I mean, this whole topic is so intense because even what we're talking, like, I hear all your points, and I've heard obviously for years. I'm aware of all these, and I understand where you're coming from, and I respect your viewpoint. And the whole globe model does have like a lot of layers to it that have kind of that click together in a way, the way they try to explain it. I mean, the question is it true or not, though? Is it actually the truth or not? And I was just thinking, too, like, what's so wild about our positions is how different they are. Like, if, let's just do the hypothetical. If, I'll go me first. If I'm wrong, let's say, just doing ifs in terms of being neutral in terms of the convo. So, like, if I'm wrong, then, oh my gosh, like, I actually am on, let's just say, hypothetically, I am on a huge ball. We are moving at those speeds. NASA, they're going to the moon, all that stuff, which I don't think they're doing and I don't think they have done. But like, think about how like wrong I would be, but then flip it. How wrong would you be? You know what I mean? If you think you're on a ball and you think NASA's going to space and none of that's happening, we actually are on a stationary plane. And I'm not trying to say like either of us like need to be deemed like crazy or geniuses. Either way, it doesn't matter. Like whether one of us is right or wrong, in that sense, or any kind of like mocking, ridicule, nothing like that. But just how, what the implications are for that too. But just that one of us is like completely wrong and one of us is right. Unless there's some third option, I guess concave or some other, I guess there's but or something like that.
Velociraptor Earth or whatever.
Well, I guess it could maybe one like a stationary ball. I mean, that would be one that would be a little different too. Geocentric ball sphere kind of thing. That would be like in the middle, I guess. It's that the Earth isn't in motion, but it is a sphere. Which I mean, I don't think is the case, but and that one has all kinds of other issues, which is why they kind of had to, I think, kind of cook the books in a way over the years to keep evolving it so that it would fit enough. But and obviously, if you're wrong, it has huger implications too for the state of the world, because there's all these industries, and so you get into that whole thing. Whereas if I'm wrong, it's like, okay, there's not that many people. I mean, I'm in a smaller category of people, like in terms of a stationary planar type of cosmology, Earth perspective, and the society has already been trained to think that it's wrong and outdated or stupid, whatever, all the kind of programming that goes with it.
A lot left to lose in that respect. Yeah, no, I totally get that. It'd be insane if I was wrong, because like the principles of physics have built up, like everything, like all the technology, every piece of technology that you have is kind of formed from what we know about physics, and it would be ridiculous. It would be absolutely insane, especially to me as someone who studied these things. If all of these things, which like these are things that we know work, like a lot of the things in physics we know work, completely unrelated to flat Earth or gravity or the spherical Earth, just like straight up, good old physics. Like these are principles that are intertwined that basically they very, very well describe things that we know, and we've been using them to do things forever. Forever, since whatever the late 1600s in terms of like real physics.
That's what I was telling you earlier, dude. Like your physics, like it's not exclusive to a ball.
Yeah, well, I guess what I'm saying is that it seems like, I mean, a lot of the physics doesn't. Yeah, of course, like if we're discounting gravity and whatnot, then and a lot of physics works, the same way. But even without gravity, I think just looking at what we see, like for example, the eclipse, what we know about optics, and what we know about what we've seen from observations, it just like kind of points to it in my head. Like specifically, the lunar eclipse is a real big one. I know I don't want to harp on that too much because it's getting late.
Yeah, but what's the lunar eclipse got to do with all this technology you were just talking about?
Well, I mean, there's a few issues. One just quick thing. I mean, there is the Selenelian eclipses, which I know Xanax said someone would bring up. You know about that, where you see the sun and the moon above the horizon simultaneously while the eclipse is happening. That is problematic for a globe. Now they claim a refraction happening, but I have another argument for that because all the celestial bodies, they're in a position in the sky, and they don't warp out of position. Like they're in a very particular degree, and they don't just warp out of that degree and then warp out of place and back into place. So it really can't happen. But maybe tonight's not.
I agree. They don't. Yeah, it's because it's not warping. They are actually in those positions. They're just not in the positions that we see. Right. The light that we get is like their positions are how they are, such that the eclipse is happening. But it's the light that we see that's refracted through our atmosphere that is specifically. This is the globe position on that. Is that the light? And it is consistent as far as I can tell.
Well, they would be in what's called a syzygy, like a triple alignment. So like the sun, earth, and moon, if they're all spheres, like it's a syzygy. And so since they're all in a straight line, there's positions on the globe Earth that you would not be able to see both the sun and the moon because of the curvature of the Earth, but we can see them.
And but those are so the positions where you can see them at the same time are very, very particular, right? This isn't everywhere on the Earth that you can see them, because I've seen this one before. I did my homework on this one. Not really. I think I just saw it at one point. It really stuck out. But you have to be on a
Well, every lunar eclipse for someone on Earth, it is a Selenelian for every single one. But you just have to be in the right spot. Yeah,
exactly. There's a very, very specific spot where you have to be. Because, well, I mean, and also like the refractive properties of the atmosphere have to be, I would assume that they'd have to be somewhat stronger at that point. I don't know if it would happen every single time, but in any case, the way that refraction works, that I'm sure you know, is that the position of the thing is, they're all in a straight line, and then some of the light from the sun is specifically shifted kind of down through the atmosphere so that it looks, because our eyes are used to seeing, when I see something, it's straight line distance from where that light is coming at me from. So our eyes see the sun as higher up, but naturally it's not actually there. And that's refraction is one of those tricky things that I've seen a lot of people use it as like a cop out. I don't like that, because a lot of those things, like a lot of the people who say that it's refraction to explain everything, those are the kinds of people that haven't thought about it physically. But and it shouldn't be used as an explanation. I think that it should be motivated by, oh, this was the temperature, this is the humidity around here, this is what we can expect the refraction to be, and then, oh, look, it's within the bounds of this thing, and if not, then you gotta think about it harder. You gotta think about that thing harder. But yeah, what were we talking about actually?
I hear you, but I guess my quick rebuttal to it is that, okay, how if you like the zodiac, there's 12 sections of the sky, 30 degree each, and there's a degree. Now, I'm not really talking about astrology necessarily, because even astronomy uses the 13th degree of Libra, or etc. So however you break it up, they're in a position. So like an ephemeris basically gives the position of every celestial body. Right now, the moon is at this degree, the sun is at that degree, etc. So what I'm saying is that I hear what you're saying about they would be in a different optical position and so on. The issue is that they're in a particular degree. So let's say something's at 13th degree of Gemini. So let's say during this Selenelian eclipse, let's say the sun is at 13 Gemini, and the moon would be essentially like 100% opposite.
Mm-hmm.
So like in Sagittarius, it'd be like 13 degrees Sagittarius. So you'd be like the 13th degree of Gemini for the sun, let's say, and then the 13th degree of Sagittarius for the moon. So they're 180 degrees. In their full moon for the lunar eclipse to happen. And then the thing is that let's say they're both at 13. Well, it's never observed that it moves out of the 13th degree. So if it were to be refracted in a different optical position, it would have to go from like 13 up to 15 and then back down to 13. You know what I'm saying? If it actually moved out of position. But it doesn't actually do that. It stays in its, just like hands of a clock, it stays in its angular relationship the whole time, showing that whatever we're seeing is in the actual degree of the sky that we know it to be, and it's not in a different degree refracted in order for it to work on a globe.
Yeah, I mean, the position-wise, they're going to be in that same position, but the light that's emitted from the sun would hit specifically the atmosphere, and then it would be refracted such that it would look like it was in a different position. Not that it would specifically be there, right? So I don't know if,
but it doesn't look like it's in the 15th degree of Gemini it doesn't go from 13 to 15 and then back to 13, like for the refractive effect. It just stays at 13. That's what I'm saying. And that can be double checked with angles to other bodies as well. Like you can do like the moon in relation to Mars during the time of the eclipse, or the moon in relation to, other bodies.
So here's how I'm thinking about it, right? There's someone that knows like that isn't in a place where you're having this lunar eclipse effect. The Selenarian, the name escapes me. But you have someone who can actually check where the sun is, and then you have someone who can obviously like check where the moon is, and then you have someone who is kind of on that fine line that's able to see both of them at the same time, and they would just read a different position for the sun. I don't know if like the reason why they see that different position is specifically because the light's refracted. I don't know how much it would need to be refracted. I'd assume it would vary depending on the atmospheric conditions. But it's like it'll be up somewhat. It'll be up enough for you to be able to see it. And I doubt that this. I mean, I doubt that this happens. For example, when there's we're talking about lunar eclipses. When there's a lunar eclipse that's very kind of far off. So there are certain lunar eclipses that aren't perfect lunar eclipses, and like maybe 75% of the moon is obscured by the Earth's shadow in this idea. And in that case, what would happen is that one part of the Earth actually wouldn't get the Selenarian or whatever it's called. I'm butchering the name, but they wouldn't get it because the angle to the sun actually wouldn't be would be too steep and maybe the refractive index of the atmosphere at that point wouldn't be strong enough to actually let them see it. So people who could have seen the Selenarian wouldn't see it in that case. It just has to do with how solid the eclipse is and the atmospheric conditions at that point. This is something that should work in terms of I mean mentally as like a sanity check. I think it makes sense. Now, calculation-wise, I think that remains to be done. I haven't actually calculated any of these things. This is in some sense speculation, but I think that physically there isn't anything necessarily wrong with that. You would just have to make sure that it actually can be refracted that much, based on whatever positions you knew were there.
Dude, with your paradigm, so do you think like pretty much the whole world is in good hands, right?
Not necessarily. I think the world is a whatever oblate spheroid or whatever.
That's an interesting question. Carlos comes in. Yeah, that is kind of interesting to. I mean, if he believes in the globe, does it mean he has to think it's in good hands? Couldn't he still think there's a lot of corruption? But that's funny the way you.
Yeah, I mean, I don't like the elite. I don't like I think super rich people are generally bad. I think that they could be doing a lot better things with that money. I
ask you this: if the truth for like I'm just saying if to be neutral, but if the Earth is not a globe and it is planar and stationary, for you, if you in your mind when you say okay, if that's the case, would that imply to you that there absolutely is some very organized group that is behind it? Meaning just
absolutely, yeah.
Okay, yeah, because I've even asked. I have like family members that are like very like mainstream, and when I've asked them, like they've said, yeah, meaning like right now they do not. One in particular I'm thinking of, but like they said there's like not a cabal at all, right now, like it's just the open market is what it is. We evolved here, that whole thing. And I asked them like, okay, but if for sure if you had like measurements like tangible that the Earth is not curving, it's not in motion, it's not a sphere. They said that too, like yeah, there would have to be some kind of people use the word cabal or a gang or a group or a corporation, something. So you agree, but you don't think that exists now. But if the Earth's not the sphere, then it would.
Yeah, I mean, it would definitely indicate that there's some sort of manipulation going on because we would have realized by now. It would have been it would have come out in some way, and so for us to not notice, there has to be some thing, some group, whatever. That maybe it's some fucking superhuman, some super organism or something that's like, you must not know the true shape of the Earth. I don't know, and
yeah,
it could be a bunch of things,
The reptilian overlords.
Yeah. I prefer the Godzilla reptilian. I think that's my favorite.
Yeah. Well, let me ask you this too. So we were talking before about like if one. I mean, I could respond to the whole eclipse question, but maybe like it goes into a lot more nuance, and it's cool. It was like a little half debate point. I'll just in terms of our debate on the debate style of it, like let's find a few of the last word for now, because I said a few things I wanted to say, but there's more thoughts I have on it, because I do think there's some problems with the lunar eclipse on the globe model, but it fits a pretty good fit though, like for the globe model.
Yeah, that's fine. We're not too serious about it right now.
It's a good enough fit for the model, but I think there are some things. Also, the way the shadow moves doesn't match with 3 spheres lining up, but we could go through that another time. But just in terms of like, our two positions overall, let's say, or our cosmological outlooks on this, if one's right, one's wrong kind of thing. So right now, okay, let's say there is this group and they are lying to us about the Earth, and they're doing it, with the GPS system and all this stuff. And of course, it links into big pharma, to the big media, oil, the banking, all of it, right? So many layers, politics. Now, if people right now are on the Earth, just like they think they're on the globe, and that's why when Carlos said like that idea of like that you're in good hands. Generally, people think that like we're the humans, we're on the globe. Of course, people know there's corruption, but for the most part, it feels like you're all kind of doing your best on this ball kind of thing. But from the flipped perspective that there is actually a group lying to us and doing this, my question to you is that if they're like getting away with it right now, quote unquote, what do you think about the idea that they're getting away with it because people don't know they exist? But if people knew that, like let's say the one thing of the Earth's not a sphere, because it's kind of hard to get to the bottom of like the vaccine thing or pharmaceuticals, that's tough. To get to the bottom of like, did they lie about 9/11? That's tough. I mean, a lot of these things, like whatever's going on with these like past events but I'm saying the Earth itself can be measured and shown not to be a sphere. And more people see that, and those measurements can be more validated in the future. I know it's a long-winded question, but with all that being said, do you think that by people realizing it's not a sphere, they would, just like you would, consider, okay, there has to be some kind of organized group behind this, that more people would be aware that there is that organized group, and then collectively we could actually maybe, make this right? Which, I mean, I'm not suggesting any violence, but whether that means like
overthrow
not violent, but
violence.
Like maybe just have the police arrest people by the law, whatever, something safe enough, but something would have to happen, because if these are like evil entities.
Honestly, if it's a group of people, like unless it's like a really large group of people, I don't even think violence will even play into it, because the second like a bunch of people know, like they're gonna have to step, because people are gonna be pissed off about that. So it's I mean, obviously if that were to happen, they're just gonna fucking like they're gonna have to throw, they're gonna have to surrender, because you got like 500 million people that are pissed off at you. Like I wouldn't want to be them, no matter how powerful
that's
you
a
are,
very
man.
positive. I mean, that's an awesome positive outlook, because a lot of people think that they'll just double down and go crazy and try to, pull the ripcord or create violence or freak out. I mean, there's that idea too. Your idea that they would kind of back down. I mean, I hear you though. Well, because there's so many more of us than there is of them. And the thing is, like, now you're right though. How many of them are there? But let's say there's only like 10,000 of them or something, or 20,000, and then there's obviously however many humans.
Mm-hmm.
And the thing is, a lot of the humans are the ones in their military. Or, you know what I'm saying? So, and that's where like any type of like battle type thing would happen, is in some military thing. But if enough, I mean, this is very idealistic to think it could go down this way, but if enough people like, kind of, came to from the perspective that it is stationary plane and more people are aware of it, that even people in the military would be like, put their foot down, like, okay, we're not working another day until we know what's going on here. You know what I mean? Like the Earth's not a sphere, like what you guys, it's all part of the military. It's the GPS. It's what we were taught at school. I'm just saying, like, perhaps the whole world would stop for a second, put our foot down and be like, what is actually going on? So.
Yeah, I agree.
But I'm saying the evil ones or whatever, it seems like the only reason they would be violent towards us is if they have control of the military, unless they have some secret military we don't know about. You know what I mean? But
yeah, and then like whatever, like nuclear launch codes and all that. I mean, what I think is that out of the 500 million whatever people as like a minimum, if you have enough people, there are a lot of really smart and really resourceful people out there that would, I personally, as some evil cabal member, I would not want to have a bunch of super resourceful people, that could totally fuck my shit up. I mean, in terms of just straight up cybersecurity, any sort of like nuclear launch codes or anything like that, like chances are it's not going to be done analog, and if it is, whatever, you can deal with that. But like in terms of like CS, there are going to be 50,000 people on that, like just breaking in and entering and messing with them. And I just think it would be one of those things where it would be like a nice like humane thing, right? It would be a nice like show of humanity, just like overthrowing these. I love a good overthrow story. That's always fun. That's always satisfying.
Well, it's cool that you think that they would just lay down their swords, give over the trillions of dollars they've stolen from humanity.
Well, maybe they wouldn't lay down, but they would definitely. I mean, part of the struggle, I think, is poetic or romantic in that sense. But I mean, I think that we would ultimately emerge victorious with ideally not that many casualties. I think that the human spirit and human ingenuity and creativity would be able to overcome any evil ass, overlord.
Well, I mean, that's awesome to see it that way. And I agree. I mean, the humans are, especially in numbers, as it were, as well, which, I mean, the deception is good in numbers too, though, if they lie to people, and that can be work its way in numbers too. Because I guess humans kind of work in these big kind of almost like group consciousness groups kind of thing in terms of our views on things. But
there's some self-reinforcing there. Actually, you can model that pretty interestingly. There are certain kind of mathematical models where if you kind of give it a little push, it'll just keep going and keep going, and so those are it's a concept in nonlinear dynamics. They're called supercritical and subcritical bifurcations, and they're really interesting. Anyway, yeah, there are a lot of really neat population dynamics models in mathematical physics and in mathematics that are. Anyway, yeah, you're talking. Sorry.
Yeah, no, it's just what was I saying?
Yeah, sorry. The autism. My fault.
No, man, you're all good. Well, I was just saying. Okay, from the perspective that, like, because you were saying, okay, if the Earth's a sphere, it's possible that there's not like this. Is that your view? That okay? Do you currently think there is like a cabal like this, or some kind of group that's running like all the major countries, the media, the banking, even the war machine? That's all done through like one corporation. Like, are you're thinking that's not the case right now?
I don't think it's just one thing. I think it's easy as like humans to think that it's just one thing because that's probably the easiest. It's the most simple thing, and we tend to want to like unify things, and it's a lot easier to fight against one force than a bunch of scattered forces that all tend to have a negative impact on people. I would like to think that it's just one group so that you have one enemy. But unfortunately, I don't think that's realistic. I think that in order to coordinate all of that, you would need a lot of well, you need a lot of money, which I'm sure a lot of people have, but you need a lot of money, you need a lot of preparation, and I just don't think it's there's part of me that does believe it, but ultimately I think that a lot of the negative things that we're seeing and a lot of that stuff is just it's more of a cultural force and it's more of a societal force that is partially basically it's partially catalyzed by them and they are the source of it, but it's self-reinforcing in that same way where they kind of do some stuff that kind of negatively impacts people and then they just keep going with it and they keep going with it. And I just think it's much more complicated than just one evil group trying to control humanity.
Okay, and then quickly, like, but if the Earth shape is not the sphere and it is, let's say, stationary,
in that case, definitely it's just one group. Like, yeah, for sure.
Or that there has to be at least like one major, because I mean the GPS system, a lot of these major countries claim they're going to space. India on the moon, all this stuff. So,
be a unified, coordinated thing. It would have to be. I mean, it would be one. That would be the easiest, because plenty of countries don't get along, and that's not even like a surface level thing. Like culturally, humans just don't get along. That's just a truth. In order to get people to get along, to keep that secret, oh boy, that's going to be one. It's going to have to be one unified group like that for sure.
You think the shape of the Earth one is too big? Like all the other things, politics, the banking, like that can all be. Well, that's actually that was going to be my question though. Is like what true? Okay, so like I'm linking these things. Like you got the military, you got the banking, you got the politics. You have the media, big pharma, big agriculture. Let's say too, like the whole food situation, education, etc. Money. I already said money. So the taxes, the governments, the United Nations, on and on. Now, how much of those are like legit or corrupt, etc. But my question to you is like, if there is corruption in all of those things I mentioned, and it's making life very painful for humans, let's say, like people are starving, there's all these inequalities and issues, and the toxic foods and everything else. My question to you is, if that is the case, that there is a group behind these things and making life, not as good as it could be for humans and so on, is there any potential truth other than the shape of the Earth that could be powerful enough to actually shift the whole system? That's my question ultimately. Is there any other truth that could actually do that? If the truths about vaccines came out, or the truth about the media being, deceptive came out, or the truth about whatever, are any of those things powerful enough, or is the shape of the Earth the only one powerful enough to change the whole system and have enough people turn their heads and be like, okay, we got to figure out what's at the root of this. And then ultimately that evil being taken out of power position. That's my question.
Yeah, well, I mean, I see what you're asking, and I mean, out of the ones that I know, it's probably the most whatever the most powerful one. I think I see what you're trying to say. But I mean, I could basically not make something up, but there are also way crazier theories, I'm sure. That if it got out, it'd be like, holy shit, everyone in the government is actually a turbo Nazi, and they're whatever. I can't even make it up on the spot. It's too late for me to have any sort of creativity. But like, just I guess just because it would be, we're kind of doing a converse statement here. We're saying, well, we're implying in a certain sense that Q implies P. If this were true, then we would see this whole thing. But if it's not true, then right, if the Earth was flat, then yeah, this would be the only, or this would be the biggest thing that would require all this unified this unified group of people to control everything, and it would be the biggest deal if it got out. But it has to be true in the first. Your your proposition has to be correct.
No, I know. I mean, it is, I guess, just for the discussion's sake in the realm of hypotheticals. But I mean, there are a lot of people that think this is the case, that there is I mean, because for the Earth not to be a sphere and for the ancients to be right, that it actually is planar and stationary, and then for there to be some kind of evil cabal that's put together this globe thing and then sold it to humanity and everything else that's gone with that, it would imply that this is the case. And then, and then the question is like, what truth could come out that would actually get enough people to turn their heads? So that's kind of why I was asking, because just like in big pharma, like it's hard to get to the bottom of like what all is going on there, like in, et cetera. The banking, I mean, yeah, you got the Federal Reserve and the way the system's set up, but
low-key big supplement. Look into like supplement companies, because it's not as mysterious or as like evil, enthralling kind of as the whole like the big pharma thing. But I mean, big pharma has actually been overshadowed now financially as a market compared to the supplement market. There's more money in circulation in that realm, which is pretty insane to me. And it's also just unregulated. So you just have a bunch of people just scamming and like selling, but they're not selling like dangerous stuff. The whole thing about big pharma is that they're selling you poisons and stuff, and they're basically making money off of it. And in the supplement industry, they're selling you shit that's like completely unregulated, so it could be poison. I said completely. It's not completely unregulated, but like very poorly regulated, and they could be selling you poisons, and they could also just be selling you a placebo. But you're paying money for something that isn't like well tested, really. And that just my brother fell for like a scam from one of those like from a supplement seller, and they tried to have something done, but nope, they no liability. It's absolutely nothing. It's kind of insane that they can just get away with that. But so they're one of those things that is probably a little bit less flashy or interesting to talk about, because I guess it's like, yeah, it's whatever. It's like supplement stuff, but like they low-key are like super predatory, not cool.
No, dude, I actually hear you on that topic. I actually was really into supplements like in my 20s for some years there, just in my own like health journey and healing journey and everything. So I was very into them for several years, and yeah, like had tried all the different types. I mean, I didn't go like too experimental because there's some really wacky ones in that whole world, but it's pretty interesting too. Like, and it actually helped me learn a lot about all these compounds, in terms of just, like glycine as an amino acid, right? Like, by being aware of the glycine supplement, amino acid glycine, like L-glycine, I then researched glycine, and then also took it and tried it and stuff. So, I mean, I think now just like raw milk is just like a better source. I mean, in terms of nutritionally, to get the amino acids in the better form than they are in the supplements, because we do need like high amounts of those aminos, and it's hard to get from like meats and other things. Pasteurizing the milk unfortunately damages it. But anyways, I'm not really talking about the bacterial question about raw milk. I'm just talking about nutritionally. But anyway, so I was really into supplements back then. So I do hear you. Yeah, there's definitely danger to be had there, and the corruption there. So yeah, I'm aware of like what you're talking about, and yeah, it is a concern, and people swindled and ripped off and poisoned in some cases. Yeah.
Yeah, there's all sorts of nasty stuff that happens with everything, honestly, but definitely some things more than others. Yeah.
Well, I guess I mean the overall thing I'm saying is that like from the perspective that there is like the shape of the Earth question brings in, okay, if it's not the sphere, there would then have to be a group that is very connivingly deceiving humanity. I mean, they're really doing it with a lot of gusto. I mean, they're the outer space thing, the satellites thing, the GPS. I mean, this is not just like a weekend side job that they're doing. Like this is obviously like major. So I guess like, and I realize the shape of the Earth question is at the like crux of that, because like you're saying, like if it's not the globe, then there would have to be some group. But what I'm saying is that if there is that group and they're, stealing tons of money from us and happiness and people are homeless and people are starving, all these issues on Earth, if it is due to this group that's doing this to us, and this group does exist, then the quicker humanity can be aware of it, the better. And what I'm saying is that like that's why I was asking you like about the shape of the Earth question. Like, is there any other truth that could come out in any of these discussions that would actually get all of humanity to turn their heads and be like, okay, what is going on? We got to get to the bottom of this, evil cabal that's running our world. Like, come on, like we gotta figure this out so that they don't do this to us anymore. I'm saying that's why my question was there anything else that could come out, as it were, that would actually cause that shift? On that big of a level, even if it came out that Pfizer was putting poisons in their vaccine, like that's what I mean? That's probably not going to get to the root of it. So that's why my question was, is there anything other than just the shape of the Earth, if this group does exist, that would out the group to all of humanity? Or the group could crumble on their own, but this is more like something that enough people would have to be aware of. And that's why I was thinking, can you think of anything else that could be? And I know it is hypothetical, like you were saying, I hear you on that, but it also is kind of a, if you consider the hypothetical that it could be real, and you were saying that there's even a fraction you think the Earth could not be a sphere. So I mean, there's some part, at least, that you consider that. So yeah,
I think if you convince yourself that something is the case, then I think that this would be a kind of a convincing, not even necessarily argument, but an interesting or convincing proposition. But to me, it's unconvincing specifically because there are plenty of other, probably way wilder theories than just the shape of the Earth. That if people found out about it, they would go to war immediately. They'd drop everything and mob the White House or whatever. Just because I can't think of them doesn't mean that they're not out there. But there are plenty of other. If the basis of how believable this theory should be, hypothetically, without considering any evidence, just in this kind of Pascal's wager kind of sense. I mean, I'm sure there's probably an infinite class of theories that would be far more volatile and evil and would really make people get mad than the flat Earth. So the reasoning is just that I think that flat Earth is relatively tame in that respect. I think that if you convince yourself that, well, it is a bunch of reptilians and you know what, not only is the Earth flat, but we're on a tortoise and you know what, that tortoise was really nice and I really wanted to meet that tortoise, but they took it away from me. Fuck it, I'm going to war with the government. You could really piss some people off, and I know I'm kind of taking the piss there, but it's not convincing to me specifically because just because of wouldn't it be nice, right? Wouldn't it be nice is not I've been played too many times to get that one. Not saying that you're trying to play me, but just that wouldn't it be nice? I'm immune to wouldn't it be nice, I fear. That
no, I hear you, but I was more
that'll
bringing
never
it up.
work.
No, I hear you, but I was not really bringing it up like in terms of like daydreaming. I was more bringing it up in terms of like the logical consequences of these things. That's more what I was asking. Like, let's say you and I were sitting here and we're like, oh my gosh, I think there's an evil group. There's some kind of criminal group that's really messing up humanity, and we gotta let everyone know. That you can see it that way, and it's like, okay, well, what truth could we reveal to the world, kind of thing, if you're going to see it in that way, that would actually get enough people to do something about it, to figure out that there is this group that's doing this to us. That it was more just in that, like the logical consequences of that. And
yeah, I think logically it's I mean, it might even be shakier logically in my eyes, just simply because logically, right, you'd be assuming like if we're talking about strict like first order logic, then you have your proposition is that there's this cabal, there's this group, and then logically what would follow is that you would look for the most reasonable, I mean, crazy thing that would kind of warrant this group existing and people uprising and things like that. But you still have to, you're assuming that they exist in the first place, but you have to first show that they exist in the first place in order to. It's not. I don't think that logically it holds up as well as just looking for evidence for the flat Earth. I think that it would be, if the flat Earth were a thing, then you would have the cabal. If the cabal was a thing, then yeah, I mean, probably the flat Earth might be one thing, but it could be a bunch of other things too. A cabal could exist for plenty of other reasons that maybe we don't even know about because they're so good at hiding it, right? So I think that neither actually gives specific evidence for the other. I think that once you have very good evidence for either the cabal or the flat Earth, then you would actually you would have it would be more convincing for me, kind of no matter what, if that makes sense.
Yeah, of course. Yeah, I mean, for it to be like, for you in your current viewpoint, for it to be more like real and palpable and actually something that would be a future of reality or something. Yeah, you would want. I'm trying to understand your perspective. That would make sense. Well, let me ask you this other question, which is also just in the realm of this. If, like, do you have enough interest in this that if there was a research team that had the quest of figuring this all out and paid well, would you feel enough passion within it to want to be a part of that, to get to the root of it, even if it did mean that the Earth is not a sphere and the whole world's going to change? And like, is that something you feel enough passion? Like, if it was as much pay as your job or even more, whatever it was, like something very, realistic in those ways. Like, are you passionate enough about wanting to know, not necessarily is there a cabal, like that's kind of a side thing, whatever that is. But I'm saying, like, let's say the truth about the Earth or physics, ether, interferometry, like a lot of these other gravity, like discovering, etc. Do you have enough passion in it that you would want to be a part of that, of a team like that? I guess, it just kind of in relation to all of this and, this being discussed, and if it was ever reality to come out, like, even if you still didn't think it was going to be the case or that you were going to find anything, do you have enough passion to want to open the door if it fit into your life professionally? I guess that's the way I'm asking that.
Yeah, I mean, if it's a job and I'm getting paid to do it and I get to investigate reality, then that's kind of my whole thing. I mean, I investigate reality to understand it better rather than strictly to investigate it. But yeah, I've always been interested in getting to the bottom of things in that sense.
So you have passion even in these kind of areas of what we're referring to, like cosmology, but also, I mean, it relates to so many other things like astronomy. I mean, like you're talking about quantum mechanics, string theory, and how like ether may be involved and how that all comes together, and like the unifying field theory, and just different trying to figure all these things out about the universe, if you want to call it that, or this dimension, this realm, the Earth, and physics, and how that all links in. Because obviously the shape of the Earth discussion is heavily steeped in physics, and however one's viewpoints are on where they land on it, it's obviously very, very interconnected. So if there was to be a new paradigm that would break some of these molds, like you're like in the kind of hypothetical what I'm laying out, it's like it sounds like you would be passionate and want to be a part of it, but you currently think the likelihood that the whole paradigm is going to shift is, in your mind, unlikely. I'm trying to kind of steelman your position, hopefully, like that it's so unlikely that it's more of like just like a side interest of popping on here and there. It's not something that you feel like you would like pursue professionally. It's also kind of tough to pursue professionally right now, unless there's some independent group, because you can't just go get a job in some of these things. I mean, you can in fields that are going to be related, but they're going to be more kind of in the mainstream realm.
Yeah, I mean, if I'm going to be researching this and getting paid for it, it's not. I mean, that's not going to happen. If you're thinking that I'm going to kind of formalize some of the things that you guys might be maybe like thinking about, but maybe you don't have whatever 5 years of math under your belt to specifically put it into theoretical framing. If your ideas have merit and they check out, then I see no reason why not. But the thing is that I won't I won't sugarcoat anything. If something doesn't look like it'll work, I will tell you, and I will tell you why. But also, I am going to be very busy for a while, so I wouldn't count on me being free to do stuff or very consistent, at least as of now.
No, but I hear you. But I mean, I'm kind of, again, just kind of bringing it up more in the kind of trying to understand just the perspective that you have in terms of like your interest, because you're saying how like unlikely a lot of this is versus, because you were kind of saying before, like you don't really want to put your energy towards something unless it really seems like if something's unproven, it has less interest than something that you're trying to discover in a way. I mean, I was trying to, kind of getting that from what you were saying earlier in a way, which makes sense. Like if something like, okay, if there's some group that says pigs can fly, and my likelihood that pigs fly is so low, I'm not going to be like, oh, I'm going to, there's going to be very limited. I would probably put no time to that, to be honest. If some people say pigs can fly, I would just be like, okay, they don't have wings, they don't fly, unless there's some, I mean, I guess I'd hear what they're saying for 5 minutes, but other than that, it's like, but
yeah, it has to do with interest. It has to do with how interested I am in it, and the shape of the Earth is something that I mean, in terms of my interest, I just haven't seen anything that would pique my interest. I'm pretty set on, okay, yeah, it's not flat, specifically because there haven't been many things that have grabbed my interest in a way that I would think, oh, maybe there's something to this. Maybe I should hear this out. If someone said, pigs can fly, when it's like very obvious that without propulsion mechanisms, they're going to be standing on the ground, then I'll hear them out to see what they have to say. But if they're not really saying anything interesting or coherent, then I'm going to be like, well, whatever, man. And so it mainly has to do with, first of all, how interesting it is, and second of all, if there's substance behind it. Those are the two things that interest me. Well, I guess the two things that I would be interested in.
Yeah, no, I mean, I was more like, because I was bringing it up more to kind of just understand or kind of gauge, because it's just interesting, like just what we're talking about. And even though, like, yeah, you may not be in these discussions like daily or super actively, like, because I think I've seen you pop in here and there, but kind of like months spread apart. And I think you said that earlier, you kind of pop in on occasion. So that's why I was just I mean, obviously it intrigues some people more. I mean, there's some like PhDs that are coming in here all the time, sometimes daily for years and so on. So I mean, everyone's kind of different at a different level of and so on. And many of them don't think the Earth is planar and stationary. They have a globe Earth view. Now there are a lot of related topics we discuss. I mean, if we're getting into like relativity and a lot of these different things and physics and I mean, we also discuss even religion, spirituality. So I mean, there's a lot of different topics that we discuss, but and reasons that people may want to listen. But yeah, I was just kind of curious as just overall, just kind of understanding your view, and because we were saying before how we have such, let's say, opposite viewpoints of what the world is, the Earth, and then the implications for it, and then we're kind of talking about how, like, yeah, that there would have to be some kind of organizing group, and then this coming out kind of thing. And I know from your view, you're saying it's a low likelihood, but then that's why I was just kind of asking the last question, just kind of gauging like whether it's just kind of interesting, because if you're not interested in it enough to be like very, very active in the discussions, but you are interested in discovering things, and that you're open-minded enough that if it were true and if it worked into your lifestyle in some way to be a part of it, you would be open to being a part of it. So that means that you must have enough interest. Like, because here's the other thing: if somebody was going to hire me or someone to like go study whether pigs fly, see, I would question, be like, well, wait a minute, like, what am I doing here? Like, I don't want to just be dedicated to something that's, what I mean? That's just, just because someone has money to pay me, if they're just completely delusional or something, I don't want to, what I'm saying? So like, there is a limit. Like, I would want my passion to line up with what I'm being paid for. I'm just using me as a hypothetical example. Like, one would want their passion to be aligned with it to enough of a degree, obviously. And then you got your integrity too, that you wouldn't want to, be involved in something that's lacking integrity, obviously, on that level too.
Well, yeah, I think that goes for anything. Yeah, I mean, the reason why I'm not in here very often is I'm just very busy. I have a lot of things that I need to take care of, and I am a full-time student, and I wish I had a bunch of free time, but studying physics and mathematics takes up a lot of that time. Not like I don't enjoy it. This is one of those things that, like, this lines up a lot with a lot of my passions, and so that's specifically why I'm very interested in getting to the bottom of things, and they're such beautiful kind of connections, and with mathematics, it's just one of those things where it's like obvious to me that I should do it. I don't know if you've ever been lucky enough to encounter a subject where just something where you're like, well, obviously this is what I'm going to be talking about and thinking about for the next, for the rest of my life, because how could I not? This is just like a natural thing for me to do.
Absolutely.
That's how these feel,
No, it's amazing.
And so I'm going to keep doing this regardless, I'm going to keep doing this, and whatever else I do, ideally it'll be at least tangential related, some way I can bring it back to math and physics.
That's amazing, man, because I feel your passion, and that's awesome to have a passion, just like a flame burning within you of either wanting to know or learn or advance things, because not everyone is tapped into that, in their own lives. Some people sometimes are seeking it, or they don't quite have it honed in. and yeah, I know where you're coming from, like in terms of like that level of dedication and focus. Well, let me link it in here, like from the perspective of the shape of Earth and your interest in physics and a lot of the everything you're doing. Would the shape of the Earth, if it's not the sphere, would it be important enough that it would have to be incorporated into your conclusions eventually, if it's the truth that it's not the sphere, to the point where if you really want to get to the bottom of things? And I guess my question too is like, how would it play into your understanding of gravity and some of these different, quantum fields and some of these different components? Like, would it be easily adaptable, or would it, or are you open to the possibility that it could like blow the whole thing open and actually get a lot of the truth and foundations to it settled out? I know you're saying that you think the likelihood of that is low, but like how it plays into physics.
Yeah, I think that if the Earth is flat, then that does certainly call into question a good deal of things that we know, and naturally we'd want to if we figure out, oh look, actually the Earth is actually flat, then we would just study that would just be a new part of physics. We would just study that. We would probably change. We would probably have to change a decent bit of our theories, like whatever optics and cosmology and general relativity and things like that. But at the end of the day, I think that physics would still just be the study of, like, we would just study the flat Earth, right? We would just study the new system. Physicists are generally just like a kind of a type of person that just wants to do that, wants to just study those things. So, I mean, if that's the case, I think it would definitely, like, sure, it would change a lot of things, but there's still like plenty of areas of physics that would be more or less left untouched. Though the behavior of light and obviously a lot of the speculation and all of that is maybe just you guys, but I think that based on what we do know about physics right now, there would actually be, maybe I take it back. I think a lot of things would be different. For example, electrodynamics would have to change because of the way that we would interact with light and the way that I guess we would classify things. It's oh man, it's getting late, so maybe my explanations might not be sufficient, but I think that would change things, obviously enough for me to be even more interested in physics. I mean, I'm just interested in studying what's going on, regardless of whether it's a flat Earth or a globe Earth. I think that everything points to a globe Earth, but I mean, even if we find out, oh, that was wrong, then I'd be like, well, then I'll study the flat Earth. Fuck it, it's I'm studying what's around us, regardless of what I think the shape of the Earth is.
Right. Yeah, because there's different levels. Obviously, you have your like physical, tangible world and everything that works in engineering and so on, and then the shape of the Earth kind of more goes into like whether there's curvature over a long distance, and then the mapping, and then it goes into what the sky is. So yeah, you get into those realms. Whereas yeah, I mean, just studying physics directly, like you might be able to do work in what they call gravity, let's say, without it necessarily having to link to the actual shape of the Earth. Whether it's pulling down to a plane or whether it's pulling to the center of a sphere. It's there's still the downward vector and so on.
Yeah. It's I think it's difficult to say exactly what would change, but yeah, there would certainly be big changes, and exciting changes. A lot of people seem to think that when there's like a big problem or inconsistency in physics, that we're all sad and like scared of it. It's a big thing, and I know that with like dark matter and a lot of those things, people tend to be like, well, physicists are they're just patching stuff up. They're just they're not actually facing the problem. They're just patching stuff up. But I really mean it when something breaks in physics, when we don't understand something fully. That is the most exciting thing, because knowing something is kind of boring. Once you know something, it's like, well, I don't have any more questions to really ask about that. And that sucks, at least for me, and I think for a lot of physicists that I know, that is just the worst case scenario. Once we figure everything out, that will really suck, because we won't have any more interesting questions to ask. but also not like, you know, we want to learn things. That's the interesting thing. Um, so it's the learning, it's the you know, learning more and more, and really understanding that that's important to us. The whole thing with dark matter, that's really just a like an actually a very difficult problem. Like there are just certain things that are just really hard to figure out, and that's why there are so many different theories and hypotheses about dark matter, and ultimately I think it's fair to say that like communally there is like a community in physics, like kind of a community, like every society, every community will have some sort of norms and stuff like that. And one of the main norms in physics is that like we're not always interested in utility, we're almost always interested in understanding the natural world. And that's like an unspoken but also like very, it's like almost like an obvious thing. And specifically when talking to other physicists, it's like if you say, you know, I'm just interested in studying the natural world, they're like, well, yeah, you're a physicist, duh. And so when people this like obviously it from my perspective it's more um like at least silly to me when people are like, well, you know, they don't actually care about the physics, you know, they're in it for the money, or what money, they're in it for like I don't even know the reasons, so for one thing or another. I, I just have to be like, you know, I've hung around these guys. That's from what I've seen, that's just not it. And you have to believe that at the very least that we're really trying to understand reality, that we're not trying to keep things, because I've heard so many things about people that like cancer researchers are like, oh well, you know, they're hiding the cure from us, and they're not actually researching anything, they're just hiding the cure from us and making money. And at least there's like some mode of reasonability where it's like, well, you know, they would be making money, and they'd want to capitalize on that. But with physics, just take it from me, we're just a bunch of nerds, and we're all just really interested in figuring out reality, even if that doesn't line up with what you think reality is. Trust that we are that is our goal, is to understand reality, and we're not like we're not just, you know, sitting on our hands.
No, I hear you, but it's just within a certain framework of what's kind of allowed and acceptable and what's being funded.
Yeah, the research environment is kind of shitty, but I mean that's that with you know, recent events and whatnot, and you know, that's it hasn't become any easier. And every physicist wishes that the research environment was better. Nobody likes having to, you know, the publish or perish mentality. I think that's the thing, is that the way that research is being done, nobody really likes it. Nobody feels that sort of satisfaction from it. People would much rather just like be funded well and then just be able to lock in and study nature. But human society gets in the way, I fear.
Well, yeah, I mean, like in the extreme example of these two scenarios, like one of them is that there is like a cabal of sorts or some kind of organizing groups, and then like there is kind of a control, but then they like allow people to study certain areas and allow people some leeway. I mean, obviously in the education system, and then finance the, you know, certain research, especially when it comes to like pharmaceuticals. Obviously, it's like very controlled, but that there is some leeway for inventions and things to happen. And then in that idea, they're like kind of keeping a watch over those things, you know, and if there's anything that they might need to be aware of or whatever, they would do that and keep monitoring, but generally kind of let, you know, these fields kind of do their thing. But whereas in the other side, it's the idea that like everyone just has their best intentions and is working, you know, in the most free way that they can. And also kind of could be both. I mean, there's certain limitations in certain fields, but because, yeah, I mean, I hear what you're saying. I even though I do think there's many deceptions going on, but I think it's kind of compartmentalized at different levels to the point to where, you know, people can be building, let's say, satellites, you know, working, you know, in companies related either in, you know, with NASA or related to NASA. They can be building all those things and actually be inventing all kinds of new parts and new things. But then the question is that thing actually going to free fall around a sphere into space, to free fall around a ball? You know, is that actually what it's doing? So there's like a compartmentalization factor potentially, you know, that separates between what we can even do, you know, like, I mean, even like a doctor that, you know, goes to all the medical school and does everything. I mean, he's not going to really know everything about what those chemicals are actually doing to the body. Like he has to go off someone else. And then, so there's kind of compartmentalization. But because I hear you. I mean, I think people are doing what they're passionate about, and they're not all deceiving or anything necessarily. I mean, there could be there obviously is corruption even within like the kind of civilian population, but I think some of these deceptions that are going on, but I know that then there's the question of the meeting place. Okay, well then how does the deception interface with the public, the people that are going to doing these jobs, and how could they hide the whole shape of the earth from all these people that are getting education and doing these jobs? And that is a big question too, that is intense to consider.
Yeah, and I think a lot of the kind of corruption that you're thinking of is likely more so due to human nature than some evil cabal. I think that a lot of that I think a lot of it can be attributed to just people. Some people will just be greedy, and some people will just be bad sports. Some people will just suck. Because not everybody in physics is like, obviously a lot of the people that I've talked to are like that, but I'm sure that there are some that maybe they're not that into physics. Maybe they're not as into physics as they thought they were, or maybe they're only in it for the money or something like that. And so yeah, they're different people with different motivations, but in physics it's actually the reason why I don't think that there are that many people that aren't into it because they really like doing it and they really like studying physics and studying nature is because it's so fucking hard that you'd have to be insane to spend that much time and resources studying this shit in order to just like, if you don't like it. I think that would be genuinely insane. Like actually crazy. So it would just be unbelievable for me. And in that case, but I guess in terms of like the engineers actually inventing things and making stuff for satellites, if the principles on which like they used, so when you do something new in engineering or in physics, then there are principles that's usually based on. Sometimes you'll have something that's like totally out of the blue, but a lot of the times these are built on centuries of research and principles and like how do circuits work. All of these things need to kind of be taken into account of, and so there is actually an interlinking between all these concepts and other concepts in physics, and so it's this whole kind of domino chain that like at what point do these concepts that do lead to tangible inventions and solutions, at what point do those actually lead back to some of that theory that maybe we thought wasn't, or maybe you guys were skeptical of? At what point does that lead to that actually being like, oh well, you know what, maybe there is actually some merit to that? And if I can be allowed to answer my own question here, I think it's when you're given kind of like some nice examples of stuff. And for the life of me, I can't come up with one right now. But if I think that if you see a tangible advance in a field based on some principles that directly link to, God, let's say whatever, we'll say gravity because it's the easiest one. If that links directly to gravity, and it's like, well, without this understanding of gravity and without this way that we think that gravity works, then this thing would have never happened. This thing would have never worked. Then it's like, well, maybe that gives that idea some more merit. If you can accept that. That's the way that I think about some of these things, where it's like there are, at least to me, there are so many advances in these fields that are interlinked that it would be really difficult for all of these advances to be able to happen without a lot of the things that we think to be true, to be true. And if they're not true, then they have to be at least partially true, because I mean, the thing that explains all of it has to at least get all of those other things right. And I just don't think that the space of possible things that could explain whatever you want to explain, I don't think that space is actually as big as a lot of people think. I think there are a lot of constraints that people aren't really taking into account, and that really that kind of whittles down your options in that sense. That was a lot of talking with maybe not so much of a direction, but I need to go to the bathroom real quick, so I guess I'll leave you with that.
All right, man. Yeah, no, if you're jumping off, I would just say maybe at my closing thought here, just if you're not going to come back, I would just say, I'll just keep it brief unless you're going to come back at all. But well, it's just like from the Earth shape perspective, I would imagine you would agree with this, that if, like currently, let's just say if it is a globe, there's some tweaks and modifications that are always going to have to happen within science and within all these fields. But if it's not if it's not a globe, then there would have to be probably a bigger rehaul and a rehaul of science and figure out, okay, what was false, what was true, and a whole like new age of that, basically, of going through all of these sciences and really figuring out where the corruption was, what parts were true, what parts were assumed, what parts only had partial data, and kind of do a finer, deeper kind of combing through. So I'll kind of leave on that briefly, because if you said you got to go, but I mean, is that kind of a final thought? Like, you would agree that there would be kind of a consequence of that?
Yeah. No, totally.
Yeah.
But yeah, no, it's definitely something to think about. And yeah, I'll be on here, more frequently. I wouldn't bet on it, but I have to work on my thesis and my research and plenty of other things. But don't be surprised if I pop in every once in a while. I'll at least be in the text, and I'll be in the chat maybe.
Yeah, no, I think
more often.
Well, I think your jumping in today was kind of a breath of fresh air, because during the Celestial Theodolite event, I think something you typed, they read it on the live stream, and they were all like appreciative that you like kind of steel-manned it and gave a very clear, lucid response. Because sometimes there's people that are, kind of giving some of the same responses, or similar people that are frequent and so on. So yeah, I think it was kind of a night. It was just a great addition, and I think I think it was a breath of fresh air for people.
Of course.
Yeah, and you're very cordial and all that. I really appreciate that, and you have a lot of knowledge.
I try my best.
Yeah, man, appreciate all that.
Yeah, I guess whenever I see something, and I had to reread I forget his name, but the person who posted that, the thing that I responded to, I had to read it a couple of times because the wording was a little bit difficult, but I did recognize that I didn't want to just dismiss it as like whatever, a word salad or something, right? I should at least check. And that's one of those things that you just look dumb if you say, oh, that's a word salad, and there was actually something that was being communicated. I think we need to be better about that. But also, I think communication is an important thing, and I think that paragraph probably could have been. I think it could have been formatted a little bit better, but ultimately, it's relative, and I think people should try to stop dismissing things so quickly. Okay, yeah.
Before you leave, I want to give you a comment. It might be useful for you. So you said that you're working on your thesis right now. Is that right? You're working on your project. So the point here, the project that you're working on is, I'm not sure, but this is how it works. Normally, when scholars, students, when they want to choose something to work on it, they have to choose between some given topics. You know what I'm saying? So the area of your research has to be within the university curriculum or within the university interest. Now, let's say, for example, somebody wants to work on the shape of the Earth, which is completely out of any, topic or any subject in any university. That person cannot do that by itself. Or if, let's say, somebody has a new idea or a new theory, again, he will face the same problem. Why? Because when he enters in any institution, any academia, he has to follow the narrative. The narrative is given. So I know a lot of physicists like to work on physics. They think it's about nature, but I don't necessarily think that they're really working on the nature, because of the presumptions, because of the narrative that is given to them, and because of the constraint that they have. So it's the areas that they can choose and work on it is very limited, and it has to be permitted by the university. Now, as I said, if somebody wants to do something, this is so important. This is so important. You know what I'm saying? Yeah. So that's the problem. So if you think that we are working freely on physics, no, I don't think that we're freely working on physics. We're not. We're just following some narrative. And I do understand that we have some degree of freedom to do whatever we want, some maneuvers that we can do, going to some other topics. But at the end of the day, you have to be on the track that they want. Otherwise, you would not be recognized. You would not be permitted to work anywhere, or you would not be heard. Yeah.
Yeah, I mean, I definitely no, I hear what you're saying, and I can see where you're coming from. A lot of research direction is actually a lot more independent than you'd think. Obviously, the shape of the Earth, since it's something that's already like in scientific circles, it's already been established. They're like, well, they wouldn't stop you from working on it necessarily, but it would be difficult to find an advisor that would be interested in that because they in their eyes it's already been solved, right? And if you wanted to work on it, and you publish things in that, I truly think that scientists are sometimes difficult to warm up to things, and it's only human nature that they'll cling on to their old theories and things like that. But if you have a very strong case and you are able to communicate it effectively, at the end of the day, they're still humans that will see that, and there's at least some percentage of them that will, take it at face value and believe it. There's a very bad example of this in a Japanese mathematician, where there's a conjecture called the ABC conjecture, that is a conjecture everywhere in the world except for this one city in Japan where this one mathematician lives, where he says he's solved it. And when people were like, "Oh, you solved it? Cool. Show us the proof." He in math, there's a very specific way of doing things that it's axiomatized in a specific way, such that everything is very clear and formal and precise, because we don't want misunderstandings and things like that. Everything is very straightforward and structured. And the way that this guy did it was so completely bizarre and also like 5,000 pages long that basically he had failed in the communication. His idea, his proof may have been completely correct, but he totally failed in the communication department. And that's like one thing that I've been having to come to terms with, is that not only is it my job in physics to study physics and to do research, but it's also and understand the world and all of that, but it's also I need to be able to actually share my ideas in a way that are tractable. And I think a lot of the issues that people run into is that without the proper kind of physics training, in the sense of not like not in the sense of like dogma and brainwashing and things like that, but if you want, you don't have to study like or believe certain things about gravity and things like this, but like you give it a shot and you look through it, even with the knowledge that actually I'm not going to let them convince me of anything. Be skeptical, but if you go through it and you learn the mathematics and you learn the physical concepts and you go through all of that, then you basically have to adopt their language. But your results don't need to be shackled by that. They don't have to be constrained by this language. You can still in their language. I think this is the best way. If you have a very strong argument for the flat Earth, then you
But your
want
argument
to
needs to
make.
back up. Yeah,
Sorry.
your argument would have need some evidence. For example, let's say I want to publish a paper for let's say the geometry of the Earth. I want to work on that, and I want to publish a paper. I would need 100%. I would need references. I would need some previous research. I would need some scholars who worked on it. And if I don't include all these references and all these citations inside my paper, I would know the community or the referee team would have definitely reject my paper. Why? Because we know that the papers recently, when you publish a paper, the more you get references, the more you get evidence. And when I'm talking about evidence, I'm talking about the academic evidence, like other journal papers that people have published. The more you give you include these things in your paper, the more valid and the more credit you will get. But let's say you're working on something so strange like the shape of the Earth. You want to say that, okay, I want to work on the shape of the Earth, and my theory is that the Earth is some of 3D geometry. It's something, it has more dimensions. Let's say Earth has 4 dimensions, 5 dimensions, instead of a 3 dimension that we know. And if I want to work on this, I know that there's not a single a paper or something that would have back up my evidence. That's going to be something very new. And I do understand, if I go with a very strong argument, let's say I publish 5,000 papers with a lot of evidence, again, it would not be recognized, or it would not be seriously read by other scholars, because I haven't included any references. And this is so important recently, at least in modern days. In modern science, we need that. You know what I'm saying? So it's very hard to come up with a weird idea without any.
Forgive me. That hasn't really been my experience at all. References are important only in the sense that if you make a claim that isn't like very, very obvious, like, okay, 1 + 1 is 2, or whatever, the sky is blue or something, then you should provide a reference for that. But that's not required. Like, for example, my advisor published like a 50-page paper on a new method of quantizing conformal field theories, which is actually very impressive and very cool. He has 12 citations, 12 references on that paper. And he's very, very intelligent, and it's an incredible paper. And 12 citations, sorry, I keep saying that. 12 references isn't a lot. I've seen papers with over 100 references, and I don't think that really makes a huge difference. I think what makes a difference is the content of the paper. So if you have evidence, then you shouldn't need references because you are the reference, right? You're the one who's coming up with that stuff. And if you're doing theory, then sometimes you don't even need evidence. A lot of the time, if you're just referring to, concepts from other theories, then you'd provide references. But if you're coming up with a new theory, then, that's enough. Your idea in and of itself is enough. And that's actually exactly what it was for my advisor. His idea was enough. He only needed 12 references in a 56-page paper because his ideas were enough. And it was accepted. It was published. So this is something that might be a misconception. Of course, I don't know where you've heard that. I don't know what experiences you've had. So in other places, this could very well be wrong. But
Yeah,
in my
I
experience,
agree.
in my
I agree
experience,
with
it's purely how can you communicate that, right? How can you communicate that? And I think that the ultimate thing that's holding back, I think a lot of amateur physicists as well, is that they're just lacking in the experience of that formalism to be able to communicate their ideas. There are plenty of people that have really, really great ideas, but they need a very important thing in physics is you need to have the mathematical background for it. And that's not like, oh, you can't do physics because you don't know math. I think it's you should learn math so that you can do physics. Maybe you can't do physics right now, some random person on the street, but you can learn. You can always do it. And that's one of those things that you can do it now with the resources that we have. You can do it from at home. Of course, I think that your education would be a lot better at a university, specifically because there are people there that already know those things and would be able to teach you better if you can kind of trust them to do that. And obviously it's fine if you can't, but you can still learn those things online and stuff like that. Not like I'm telling anyone here to go do physics research, but the reason why a lot of people in physics communities like that will sometimes discard papers, other than the fact that they're usually super busy. It is ridiculous how much these guys are overworked. It is insane. Not a single physicist doesn't have eye bags. It's absolutely nuts. But like you'll,
You
I
have a
mean,
point, bro. Because I mean, I've been going in and out for like 5 minutes, and you have not stopped talking.
yeah. I do. I guess I don't know. Did you stop in like halfway through without
I came
context
in
or?
here, you were talking. I mean, I was waiting for somebody to say, answer back some kind of point, but you kept going and rambling. I left. I came back, and you're still going.
Yeah,
So
I
I'm
mean,
wondering
Kasra was talking in between. I think you just missed that.
Yeah, it's okay. It's okay. So here's the thing. So you think that there's some certain things that are 100%, like the sky is blue, for example. You said that the sky is blue. Nobody's talking about it. But let me just stop you exactly right now here. The sky is not blue. But these are the problems that we have with the science. So when you presume that the sky is blue and you go on with its presumptions, you're going to end up with a trash result because the sky is blue for human eye. It's not going to be blue for some other animals. This is a subjective phenomenon. So here's the thing. There are hundreds of these things that we have in science, my friend, that has been approved without
Well, that's
any.
not completely true though. Like this guy
Well, I
is
can tell you
this
that
guy is blue.
I can tell you no. The reason that you're picking up the short wavelength of the white light, and those are the high frequency.
Well, I mean, yeah, it's violet. So, I mean,
yeah, exactly.
if you really want to say the scattering, yeah, but you can. I mean, obviously, it looks blue to us.
Yeah, when the light
what I mean
scatters,
is
the
that
ones that
you
have
can
higher
measure it.
frequency. Yes, of course. But you're only picking up those wavelengths because your eyes is not shrunk enough to pick up the other wavelengths, which have been weakened by the
No,
environment.
you're right.
Yeah, so let me just continue with this one. So, for example, when it comes to nighttime, you think that the sky is dark or is black. It's not. For pigeons, I know pigeons, they don't have a dark time. They're gonna see like a reddish sky, even at night, even at the midnight. Not a lot of these pigeons, which they can navigate with the magnetic field, they see the sky as a reddish color. So what we see it black. And even during the day, they might see some other colors like purple. You know what I'm saying? So sky is not blue. It is blue, but that's very, very it's incomplete. Let's say it like this way. So a lot of things in physics, they just pass over it without completely figuring it out. They haven't figured out a lot of things. You know what I'm trying to say?
Reason, the reason that I mean, no, I see what you're trying to say, and I just want to say that the reason that you know that is because physics told you that, right? Because we know how Rayleigh scattering works. We know how photons interact with the atmosphere. I mean, that is physics, right? So it seems like I understand the overall point that like once we think we have something figured out, we're just kind of done with it. But I also have to I think I have to disagree here, because there are actually a lot of things that people think that they've understood, and then there's actually a lot of really interesting research that comes out of it. I hate to use my advisor as an example again, but there's an undergraduate that I was talking to, and he's also working with my advisor on specific like a more generalized formulation of Lorentz invariants in special relativity. And special relativity is something that came out over 100 years ago, and we're still working on it, right? We're still
No, you're not
looking into
working
new
on it.
things
Okay,
in it.
let me just stop here. Sorry to interrupt you, because this is so important. You're talking about general relativity and the Lorentz transformation. Let me just give you this one. This is a very simple example that all you guys can do right now. If you go to any university right now and go to the PhD research in any theoretical physics, any type of physics, right? They're not teaching anything about general relativity anymore. That's all. It's over. It's finished. So I'm
That's
going to
not
repeat
true.
that. Okay, so
I
I
mean,
personally, I was.
you can't find it there, but you can still do research in
Yeah,
it,
but
is
it's
what I want to say.
it's very seldom. It's not like 50 years ago that we're all working on the general relativity. All I'm trying to say is that it is something that has been settled down. It is something that, based on what you said, it's been figured out, and no one has been talking about it, and it's been passed. And now we're using as a presumption, as evidence, as some material to come up with more theories. But the problem that we have is that why they're not letting people to go back in time and work on, for example, on the Michelson-Morley experiment, or some other theories that they came like 100 years ago. They're not working on them anymore. I personally, I was searching for a PhD program everywhere, and I was looking for, trying to find an area of research which I'm interested into it, right? And I was interested in particle dynamics, but I was also interested in general relativity, and I really want to know that why Einstein came up with the mass contraction, length contraction, all that kind of thing, the algebraic formulation that came on. I tried to do, I know it. I studied by myself, but I know that there's not a single institution right now that they're recapping, or they're just going back to the Einstein's formula and trying to understand it again. I'm sure they don't think about it anymore. And there's, as I said, there's even the Earth.
Yeah.
So that was one example. For the shape of the Earth, we have the same problem. For the rotation of the Earth, that the Earth is spinning, we got the same problem. These things been it's been proven. Apparently, it's been proven back in time, and they are not working on them. And this is my point. I'm trying to tell you, my brother. The
Yeah,
universities,
I
the
mean,
institutions, they are not working on these old concepts that they have passed. You know what I'm trying to say? This is the point. So if they're
yeah,
working on dark
from that
matter, if they're
perspective,
working on
yeah.
yeah, so if they're working on, for example, string theory, well, what is the what do you call prerequisitions of the string theory?
Prerequisite.
You need to know, yeah, prerequisites. What do you need? You need to at least know some algebra. You need to know that what is a tensor, what is a space tensor. What you need to know all these. You need to know at least the Lorentz transformation and the matrix of the space sum that Einstein came up with it. You need to know all these things before you go to the dark matter.
Yeah,
Okay,
not to
so
mention
dark
quantum
matter is a new.
mechanics, and yeah, you need to know a lot. Yeah.
A lot of other things, yeah. So you need to accept, before you go on to these new areas of PhD in physics, what you have to do. You have to accept all these things that has been said to us, and this is the problem that we're facing right now. You know what I'm trying to say? This is the problem.
So I think that there's a reason for that, and I don't think that it's necessarily to do with academia. I really do wish that academia would support every field of research as, equally, so that you could just you could research whatever you're interested in, and that's actually my ideal. That's what I want academia to become. But I mean, it does make sense to me why academia isn't that way right now, and it's because there's a limited amount of funding. And we generally want to fund things that look like they will have advances. There will be advances in the field, and so that's why they're like hot fields, right? Topological insulators. They're really interesting things in condensed matter, where condensed matter specifically gets a lot more funding than other fields of physics, because it's like a playground for making discoveries. There are so many new discoveries that you can come up
This
with.
is where the money goes. This is where the money goes. That's
Yeah,
all it
and
is.
it has a lot of application too. But there's also room for a lot of discovery there because of the nature of condensed matter, which is that it's very linked to experiment. And so naturally you will get a lot more discoveries in that, and so there will be a lot more research funding for that. And it's not impossible to do research in general relativity, for example, because general relativity is, I mean, in any high energy theory department, you're going to have people that are interested in quantum gravity, people that are interested in general relativity. In fact, I'm doing research right now that is in conformal field theory that has applications to black hole microstates for understanding quantum gravity. And these are all really interesting things to me. And theory is not, very well funded, and it's because we don't have unlimited money, and there are so many things that we can take a look at. And on your point that we kind of pass by things and we don't take a look back at them, like as if there's nothing else to discover. I don't think anybody ever truly thinks that way. I think that's maybe how it looks like because people aren't actively researching every field. But there are plenty of things that we can keep learning about that stuff. But unless there's promise,
Can you do
unless
some
there's
research on Ether? Can you do some
on,
research on Ether right now? Do you think that you're
I,
allowed to go to university and work on Ether? This is a very
well,
simple example. And Ether, hold on, Luminiferous Ether was something that most of the physicists, like the fathers of electromagnetism, like Maxwell, Lorentz, and you probably know a lot of them, they all believe in Ether, right? Now, it's about 100 years that they're not talking about it, and they just rule it out. They say it doesn't exist anymore. Now, let's say somebody, for example, like you become, I don't know, skeptical, and you want to start doing again from the scratch. You want to do some research on the Ether, and let's say you have some masters, and you want to do a PhD research on Ether. Do you think that you're allowed, or do you think that there's any place in the university that you can do that? I'm sure it doesn't exist because I tried that. I've searched for the keyword Ether in most of the PhD programs across the world, and I couldn't find a single one. And this is the thing I'm trying to tell you, my brother. I know there's some freedoms that in the physics, but it's way more complicated and it's way more deeper than we would think. There's a lot of things that we just passed over it. We just overlook all these things. And as I said, it's very hard to go back and just study again. It's not a very easy job.
sorry, I'm back. Yeah, I think that the fact that I don't think it's impossible to do research on Ether, and but because it's kind of it's been established, at least to us in physics, that the Ether is not a thing, that it wouldn't really make sense to have a research program for it because we've already kind of determined that it isn't a thing. And so you can still do research on it. It's just
Sorry, I'm
naturally
saying,
it's not going to be as well funded, right?
who is we?
Just generally, the physics community has determined that the ether doesn't exist. But I mean, regardless, that would be the reason why.
When they said that?
I think a
100
couple
years ago.
decades after the Michelson-Morley, yeah.
Yeah. So you believe in the scientists back in 100 years ago? You think that they were smarter, more intelligent? They had internet like you, and you think that you blindly have to just accept that what they have said 100 years ago without having any digital instrument, without having the information that we have today? This is the thing
there
that I'm
have
trying to
been
tell
modern tests of the ether as well. We do have modern interferometers, and they show the same thing as far as I can tell. There have actually been modern tests of the ether. I saw a couple of papers, maybe 2 or 3 years ago. So there are modern tests on it. They're just not as popular because we've accepted it. We've accepted that it isn't a thing because even with their instruments back then, they thought it was conclusive enough. And by the way, I don't really, I don't
it wasn't accepted. It
accept
was
anything.
controversial.
I don't.
No, it was very it was controversial. No, this is the problem that the people the people like you who are in the university in these environments. Like I don't want to because I've been in these environments and I know because the thing is that for example, you're saying that you said that it's been done. It's been it's like you said that they recently 2 years ago they used advanced instruments to just come up with the same result. But the point is that if you just do enough research on this experiment, they never rolled out. They never said that the ether doesn't is not a thing or it doesn't exist. It never said that. And by the way, 100 years ago, they never said that ether is not a thing, my brother. And this is, look, I don't want to teach you right now, but I want you to do again another research on this. That why this experiment was so controversial, and why the physicists back in time divided into two groups: people who believe that ether exists, Earth is not moving, and the people who believe in the Copernicus things. So this is the thing that you guys have dismissed. Hold on. This is the thing. This is the factual history that you guys have dismissed. That you guys would have think that unanimously, all the scholars, all the scientists, 100 years ago, came to the same conclusion that ether does not exist. But I'm telling you, if you go read the history, and this is so important, a lot of physicists like you would think that it's so important just to memorize the formula, just know the physics by itself. No, the history behind physics is so more important than the physics by itself. So this is what I'm trying to tell you. Go read the history, and you're gonna understand that they never said that ether is not a thing. And there were like hundreds of scientists, physicists, that they still believe that the ether exists in that time. And I'm gonna repeat myself here again.
Sorry, can I ask a really dumb question, please? If the ether did exist, if the ether did exist, why hasn't anyone proven it?
Well, that's a good question. That's a very nice question.
He's saying because they didn't, because they said it wasn't a thing before, and they just haven't done any research on it since. Because
no, but I mean, surely there's an experiment to prove that it exists, right? So
you know what, there is.
If that experiment exists, why haven't we done it? I'm sure it's not a lack of funding.
Yeah, the Michelson-Morley experiment. I think Kasra, you mentioned that it had to do with the Copernican principle, or the Earth being stationary, So there might be. I think it's easy to misunderstand here as well. But we were very certain that the Earth was not stationary. It had more to do with detecting the ether wind. We wanted to detect if there was a medium, right? Then there would have to be a physical medium. So we postulated that in order for it to make sense, it would have to be.
Yeah. So you're wrong about here. Yeah. So what you're missing here is that you think that just because they haven't detected ether drag, ether doesn't exist. But you need to understand the reason that they said that is because they presume that Earth is moving into the space. So that was the first building brick of this whole theory, that by presuming that Earth is moving based on what Copernicus was saying, we should be able to detect the ether drag. Now, if we didn't detect the ether drag, so it means that the ether doesn't exist. This is the kind of a proposition that they came to the ether doesn't exist. The propositions and the presumptions. So somebody can argue in the first place. Hold on. This is so important. This is what you have missed right now, because you say that just because they haven't detected ether drag, it means that ether doesn't exist. But you have forgotten that you presume that Earth is moving into a space. But if I come and say that, oh, you know what? I don't believe that Earth.
Look, I'm sorry.
If I say that,
I'm sorry, mate. That wasn't even my point. My point was just about being able to do an experiment. If we have an experiment that can prove that it doesn't exist, then you must be able to come up with an experiment that proves that it does exist. Whatever you're fucking calling the ether drag
I couldn't come up with an experiment. But you guys couldn't come up with experiments to prove it.
And nobody in 200 years has, right? So
because it's luminiferous. It's luminiferous. It's very invisible.
I'm going to shut up now. That was my point anyway.
No, I'm just saying your point. But the point was trying to tell the cheesemaker he forgot that what he said was based on a presumption. So can you understand this? So if somebody argues in the first place that Earth is not moving, therefore he would not therefore he would not expect to detect any ether drag. So if Earth is stationary, Okay, cool.
Yeah, of course. I understand what you're saying. I don't think it's realistic to have I think it was a reasonable assumption to make that the Earth was moving through space. I think that from everything that we know, that is reasonable.
Okay. No, this is where you try. This is where you kind. I think that this is where, with all respect, my brother, I think this is exactly the point that you're fighting with yourself. You're convincing yourself that the presumption somehow was correct 100 years ago. But people like us, we're not like that. We really wanted to make sure out of it. Why? Because we know there were like a lot of scientists and scholars who were against this. And since there's like a lot of conspiracy running out the world, why not thinking about it again? And as I said, you said it that you didn't know that they presume that they have to say the Earth is moving in the first place, and you still think that they came up with a one conclusion. But as I said, if you read the history back in time, the scientists they completely divided into two sections, two parts. There were a lot of them believe that the Earth is not moving, therefore the interferometers would not detect anything. And guess what? They didn't detect anything. So this will make more sense.
So unfortunately, I think you might be misinterpreting something here. I don't believe that there were any physicists that believed that the Earth was actually stationary. The two camps were mainly between those who believed that there should be some ether wind, some ether drag, and those that didn't believe that there was such a thing, and of course those that were of the kind of Einsteinian view.
That to like reify the correctness of relativity theory, but like in the way that he did that, now that you now know that as his selection of the data, you can see that it was obviously to hide this to hide the correctness of Miller's work, which would invalidate special and general relativity. Now, so it should be noted here that Miller got a stronger reading than the Michelson-Morley experiments, but not that much stronger. So if the Michelson-Morley experiment was like just over one fringe to produce 6 to 7 kilometers, right? If one fringe was going to equal 5, Miller got 8 to 9 or something like that, or 7 to 10. Like there's different sources there to extrapolate how much he got, but so roughly it's like 7 to 10, or it'll be referred to like 8 to 10 or 8 to 11, something like that. Like there's variations in it, but anyway, slightly more than Michelson-Morley, right? But not enough for the full fringe. If the Earth were in motion relative to the ether at 30 kilometers a second, right? So a huge discrepancy there, and that's why they had to continually ignore Miller's work, because what he was consistently showing through ether physics is that there was no relative motion of the Earth, right? So now obviously they were interpreting these mechanisms they were interpreting the slight fringe through the mechanism of contraction, because they really wanted that Earth's velocity to be true, but unfortunately they weren't able to get any first order dependency measurements on that. So far they've only produced a first order dependency on an effect that they attribute explicitly to rotation through the Sagnac device and Michelson-Gale-Pearson. Okay, and then so when Miller plots out his data, he plots out the axis of rotation of the ether, which is really cool. So earlier, how I was saying, in the heliocentric model, the Earth has to change speed 4 times a year, and then so it's on its axial tilt, and and all that, so to speak. The Earth is in the heliocentric model. So what he showed here is like in perfect tandem with what the heliocentric model would need if it were actually in motion at 30 kilometers a second. If it had that first order dependency relationship, I mean, this guy would have been the Nobel Prize. He would have had all the prizes. Everyone would be like, "Who's Einstein?" Like Einstein's cool, but like Miller mapped out, this and proved the ether and all that. Like it would be a totally different situation if they were to accept Miller's paradigm. But you have to accept second order corrections of length contraction and all that. And then when we get into the two types of interferometry, linear and circular, which one depends on linear motion, which one depends on angular rotation to produce a fringe, we're going to see why they absolutely cannot afford to say that the ether exists at all, because that proportional variance relationship with the observer's velocity, right? So that isn't measured. So okay, so I think that's all on Miller. So this is, let me show this. So yeah, so this is his apparatus here. This is the apparatus with the shielding, and then he also had some paper stuff that he would put over these glass windows here that were protecting the light beams as they reflected over. Is there a topographical view of the light? No. So yeah, here it is. Okay, here we go. So there's a topographical view of everything. Pretty standard for. So and this is in regards to measuring linear motion, right? So for the Michelson-Morley, for Dayton Miller. Okay, and then so in 1942 we have DeFore and Pruner. These guys really threw a wrench in things. So they won before they. So in modern interferometry for the linear standards Michelson-Morley apparatuses, whoever, I don't know, the organizations who do these experiments that publish the results and whatnot and have this thing where they say that the results that they're getting are trending to zero, which prove the correctness of Einstein's theories. But what they're actually doing when you read their experiments, they've actually altered their apparatus and conducted it in a basement and everything, and basically done all the factors that Miller figured out in his controlled experiments that would force a null reading. So they literally just do all that. So anyway, they don't go, okay, this is what Michelson did. We'll recreate their apparatus. We'll maybe use some of the same parts if possible, but we'll do it analogous to what they did first, see if we can reproduce it, and then we'll build upon that, right? So almost none of these people do this. So what was really cool about DeFore and Pruner is that they were like, okay, we got to reproduce Sagnak's effect first in the way that it was first derived and all that. So the only thing that differed from their experiment was, I forget, there was one piece that they couldn't find from the original setup, but they ended up using the mirrors, and they doubled the area of the distance between the mirrors. So other than that, rotating device, same mirrors, and all that, right? So, and same wavelength of light as well. So they did their own setup and reproduced the Sagnac effect, and I'll just kind of read from the abstract here. So in a series of experiments here detailed, it is necessary to realize that we used an entire optical circuit attached to a revolving platform as the former work of Sagnac. Under these conditions, we noted that the displacement of fringes observed was in the same margin of 6%, whether the source of light of the photographic receiver are entrained as part of the rotation of the platform as these experiments of Sagnac, or as when they are fixed to the laboratory, which we'll get into further in the paper, which lead to some interesting setups. And they actually show that the location of the detector, like whatever takes that last reading, is what determines the frame. So very cool stuff. Because there's some speculation on whether if it was the last mirror before the reflector that determined the frame and all that, if it's inertial or non inertial, but it's actually what determines the inertiality of the frame is the location of the detector. Very cool. So let's see, potential platform. So this displacement of the fringes obtained under these new conditions was used to predict the classical theory. So the classical theory being the relative motion shows a first order dependence, or motion shows a first order dependence on the varying speed of light. In the discussion where the optical circuit is entirely attached to the revolving disk, as in the experiment of Sagnac, an observer has no means of making the choice in the interpretation of displacement of the fringes obtained by S, given respectively by the classical theory and by the relativist theory. But in the discussion where there is part of the circuit which remains fixed relative to the laboratory, the relativistic theory cannot remain in agreement with the classical theorist, nor with the results, assuming as he had done until here, that the center, where he must assume the position to calculate the experiment, can be chosen arbitrarily on a rotating platform. The center must be with the center of rotation of the platform. Sorry. So, quick recap on special relativity. The first postulate: all reference frames are equally valid. This is a pledge of allegiance to Lorentz symmetry, and what that means is that no reference frame is equally valid in another. So when you do a transformation equation, the laws of physics will be invariant under those transformations. So other things can change, but not that, right? So in relativity theory, the idea here is that on a rotating platform, you could derive the effect of relative motion without anywhere on the platform. It doesn't matter, right? So they're saying that they could derive from anywhere on the platform, you could derive how much light would be displaced, from your rotation or whatever, right? And what they found was the relativity could only answer it from the center of the platform. Now they act like it's chosen arbitrarily for convenience, make the math simpler, yada yada. But Paul Levoux couldn't do it. And this is the guy that invented the metric tensor for general relativity to ascribe the what's it called? The metric tensor to co-opt the Sagnac effect as a general relativistic effect with through the equivalence principle and all that, right? So yeah, this is huge because like he said, the location of the detector determines the frame, and although the rotation, so that means that there shouldn't be a displacement. The speed of light should be the same because he is in an inertial frame. So when Paul Levoux tries to calculate it, he can only derive the answer from the center of the platform, which on the relativistic side, assumes that because of you can assume that's stationary. Basically, is what they say, right? That's why it has to be the center, because that's the only point on the platform that you can actually assume it's stationary. Sorry to raise my voice. I was trying to get that out, but I couldn't get the words out. All right, so here's their setups. So the classic Sagnac, yada yada. Then they have the one where they put the observer on the wall, and here's a setup where they have a rotating platform, stationary observer, and then they have so get this. They have a rotating platform and they have a stationary platform under it. When they do that experiment, and it's in the actually I'll have to reread that. I don't fully remember that off the top of my head because it kind of blows my mind. But basically, what they showed was that there was a variance in the speed of light relative to, as if the rotating platform was translating its dependence of first order dependence of motion to change that speed of light for the stationary observer. Like it's just mind blowing. Like that right there falsifies relativity on the face of it and proves that there's an ether, because that's a translation of motion for electromagnetic propagation where there should be none. Okay, so anyway, so they have this split setup. So they would do have the detector on the wall. So they have another platform set up here upside down where they would have these 45-degree angle mirrors to accept this 45-degree angled mirror, and they would just bounce it off of this. So this one would be rotating, this would be stationary, and they would find that the effect is dependent on the rotation of this, even though this is stationary. It's absolutely insanity for relativity theory. Really cool stuff here. So that experiment isn't talked about. I haven't really heard anyone talk about it, but yeah, it's a crazy one. So Yuri Galev. So ethereal wind experience in millimetric radio wave propagation. So this guy, very cool, did radio millimeter wave propagation, and he reproduced Dayton Miller's work. So not only did he show like a Michelson-Morley variance in the speed of light or electromagnetic propagation, there's a variance to a degree that seems to follow the sun, right? So I know you're a heliocentrist or whatever, totally fine. Not the argue of contention, but we think that, or I'm coming from a perspective where everything's closer or more local, and the translation of motion is coming from that. And then obviously your perspective would be that the translation of motion is just going from a much faster speed over a much greater distance. So, not much differences. And then obviously, the big distinction, flat earther for me, globe for you. But we don't, not the purpose of the discussion here, but I just wanted to point that, or, prep. All right. So Ruyong Wang. So this is huge here. Because I think this is the reason I think that it's not the shape that we say it is, because if it's not a spinning globe around the sun in the way that they've claimed to experimentally measure through second order corrections through time dilation and length contraction to get their distance to confirm their model, I just don't believe that. And if that stuff isn't the case, then I think that we're on a plane. There's a vortex in the center, blah blah blah. Right. So anyway, so the generalization of the Sagnac effect. So really awesome paper here. What this guy did is he unwound a fiber optic gyro cable, and he put it around the what's it called here. He basically made a conveyor belt out of it with little wheels, right? And then he showed here, and then he also has a setup where the motion of the conveyor belt will also pull this little tray here that has a fiber optic gyro on it as well, and to measure linear motion. So what he also finds here is that the linear motion in this track of the conveyor contributes to the full amount of the Friend shift pattern with a first order dependence on the motion, right, on the velocity, on v, right. So awesome stuff here. Let me show. Let's see. So just to give a quick recap here. Right. Yeah. So the big thing that he found here is that the circular equation, the circular derivation for the Sagnac effect, right? Your delta t equals 4 times omega times a over c squared. So what they're saying there is just basically the fringe displacement is going to be equal to 4 times the angular rotation times the length that the total length that the light have to travel. So in a fiber optic cable where it's looped up, if you have a cable that's 1,000 meters long, your area is going to be 1,000 meters. If you have a little tiny, mirror reflecting apparatus, it's going to be the path that light has to travel, that total path, that total length. And then for the linear equation, same thing, delta t equals 2 times the velocity over the length, or times the length over c squared. So the key factor here is velocity just the motion, right? So, and then it's like, well, which type of motion? Well, he showed that these are equivalent and that they both derive the same, that you can actually derive the circular effect using the linear equation. They're completely equivalent. Okay, yeah, so that really takes away the Michelson, or with the relativistic paradigm where they say that linear motion of Earth around the sun can't be measured, blah, blah, blah. It would absolutely be measured because there's a first order dependence on that v, on that omega that produces that fringe. So if the Earth's orbital velocity existed, it would have reflected in the Michelson-Morley, in the Dayton Miller, like it would be there in Yuri Galev's experiment and in Hector Minera. Yeah. So also, in addition to the radio millimetric propagation, Yuri Galev also did optical wave bands where you could see the fringe patterns, and he also through doing this he measured the viscosity of the ether. But I am not prepared to speak on all that. I'll have to reread this and really try and get my head around it. It's kind of above my pay grade for when they're measuring the kinematic viscosity of it. But maybe you can make sense of it. But anyway, that's what he did, and again reproduced Dayton Miller's work showing that fluctuation that corresponds to the equinoxes. So it's mapped to the sky, right? And then, so an important thing to note here is, right, so on the globe, how they say that it's tilted at a 23-degree axis, right? If the globe isn't tilted in that regard, I'm sorry, that tilt matches the cosmic microwave background, right? The axis of rotation of the universe, the dipole of the cosmic microwave background intersects with Earth's supposed axial tilt, which is crazy. But another way to interpret that is that the universe is rotating around us, and this is what these people are measuring, right? So, let's see. So Hector Minera did. Okay, so what they did here is a diapetrometric, whatever this word is. What this word means is that they left the device running continuously. So instead of turning it on, taking the readings and all that, they just left it running for 3 years straight. And then over their culmination of data, they also reproduced Miller's work and showed that the fluctuations reached their minimum and maximum dimensions on the equinoxes. And their setup was extremely technical and precise using modern equipment and stuff. They didn't, they weren't messing around. So, yeah. All right. And then there's some really interesting analyses done by Robert Bennett and James Demio, like I was saying earlier. So Robert Bennett really breaks down the Sagnac experiment and the significance of that, and how it shows that the Earth is not in motion. So this guy's not a doesn't believe the Earth is the same shape as me by any means, and he's a full academic guy, retired. But he, analyzed Wang's work and was like, "Holy crap, this is insane." So he writes an analyzation of everything, and breaks down how it shows that the Earth is stationary. And then also he has a breakdown of the DeFore and Pruner experiments. Now the DeFore and Pruner experiments, and I'm familiar with the subject matter, and it's kind of like I'm on my second or third reading of the DeFore and Pruner. So, but this has been helpful in going over the DeFore and Pruner and breaking down that. So he has a summary of each experiment that they did. So when the rotor is at rest in the lab frame, the speed of light equals c in both reference frames. When the rotor moves at v in the lab frame, the speed of light equals c plus or minus v in both reference frames. Special relativity is disproven. Emission theory is disproven. Ether entrainment theory is disproven. And Gaussian relativity is supported conditionally. And he goes into that by showing the covariant relationship for the Gaussian law of additive or adding velocity. So he shows that and how that effect is in alignment with dynamics, and dynamics is supposed to be covariant in all reference frames, and the only frame that's ever experimentally verified in dynamics is the lab frame, which is stationary. So this stationary frame, which is supposed to be covariant to all frames, actually produces non-invariant transformations of motion, which break the general principle or general relativity's principle of covariance, right? So we're all, because in the general theory, Einstein expanded the covariance principle to all reference frames, all mathematics, Gaussian, et cetera, right? So, huge problem there for that. And he really hammers it home. And then this is really cool. So Sagnac and de Pruner both found that the speed of light equals plus or minus v in the rotor frame. DeFore and Pruner found that the speed of light equals c plus or minus v also in the lab frame. The optical bench is at rest in empty spinning platform below it. This alone disproves special relativity as the speed of light varies. Yeah, so very cool, very cool. Yeah. All right, well, I hope that, and I'll make all these papers available to you so you can check them out so you don't have to dig them out yourself or whatever. And yeah, let me know what you think. All right, we have a good night.
Hope you brought your flute, because we're going to be talking about the man with the largest flute collection, I believe, in history of flute collections, which was Dayton Miller. But actually, we're not going to be talking specifically about the flute, but rather the interferometer. He took what was called the Michelson-Morley experiment, the first experiment with an interferometer where they tried to measure the orbital motion of the Earth using the induction rate of light relative to the equations that J.C. Maxwell had derived from the electric constant and the magnetic constant, so that they knew what that rate of light should be-ish. They understood how that worked and how they could use that to measure the relative speed or the relative motion of the Earth, and they didn't find that orbital velocity of the Earth. Instead, what they found was a much slower relative motion. They understood how electromagnetic induction would work and how a medium was necessary for that induction to work. This is before Albert Einstein came along in 1905 and made science into religion. So we actually had logic behind how light would work and how there would actually be an absolute frame of reality, an absolute lab frame, where the laws of physics are actually applicable universally. They're not relativistic. We don't have to relativistically do science. Because it turns out when you actually go to measure those things using precise instruments, direct measurements, a ray of light in some water, some running water. Because you can look at the Fresnel drag test, right? Water going one way and the other. The water's going 44% faster, or the light's going 44% faster with the water, 44% slower against the water. So something's dragging the light. So when Miller took his measurements and found a preferred directionality to the quote-unquote speed of light, and it correlates with the equinoxes, and it's not consistent with the orbital motion of the Earth in the heliocentric model, then what is that thing that's moving? What's dragging the light? What's causing that difference? That would be the ether wind. And actually, I conceptualize of it a bit deeper, being something like absolute time. It would be like the flow of everything, essentially, because everything exists within this background medium. And the equinoxes, literally the time in the sky seems to correlate with the periodicity of this measurable ether wind. So if you wanted to look at how to measure time, the closest thing maybe, in my opinion, you could get to would be to look at this flow of this ether wind.
You said it that you didn't know that they presume that they have to say the Earth is moving in the first place, and you still think that they came up with one conclusion. But as I said, if you read the history back in time, the scientists, they completely divided it into two sections, two parts. there were a lot of them believe that the Earth is not moving. Therefore, the interferometers would not detect anything. And guess what? They didn't detect anything. So this will make more sense.
So unfortunately, I think you might be misinterpreting something here. I don't believe that there were any physicists that believed that the Earth was actually stationary. The two camps were mainly between those who believed that there should be some ether wind, some ether drag, and those that didn't believe that there was such a thing, and of course those that were of the kind of Einsteinian view. And so what ended up happening in the end was that all of the right, when you think about a medium that a wave has to propagate through, it has to have properties, and so obviously it's not going to be solid. And it's if we assume that it's a fluid, then it needs to have certain fluid properties, like how we know that fluids behave at least, or it should have more properties than that. And so what you can do is you can go through all of the properties that would need to be true in order for us to see what we do see, like experimentally. And what ended up happening was that all of the properties that the fluid would have ended up just being unphysical in the sense that they were paradoxical as far as I can tell. And so what they ended up needing to do was have something that ends up reducing to special relativity in the limit. And so ultimately, the reason why special relativity and general relativity were accepted was because the ether ended up looking exactly like them, and it was just one less assumption to make. This is historically how it turned out, and I understand that there are a lot of different pieces of information that kind of come through, and
I
it's easy
suggest you
to.
tonight, just do yourself a favor. Tonight, just talk with ChatGPT about Michael's Moore experiment. And I want you to just point out the views that I told you and see what ChatGPT will tell you. Because what I've
I
said
did
to you,
read the original papers at one
it
point.
wasn't my view, my brother. It wasn't my view. This was a view from a lot of people in ChatGPT, and I'm not saying I'm not referring to GPT. I'm not saying that's true, but at least that's not a bad source to talk with it. Now I want you to just talk with it and let him to just explain to you that how back in time this was so controversial and it wasn't unanimous. Now, this is the thing that you have missed, and you still think that all the physicists, they never believed that the Earth is not. No, they didn't believe that the Earth is moving, or didn't believe. They came to a point, a crossroad, that they have to choose something between two things. They have to either believe Earth is moving and ether doesn't exist, or they have to believe that ether exists and Earth is not moving. They only had two options. And that was a factual history, I'm telling you. And I want you to verify this with yourself with ChatGPT, because you're not the first person I'm talking in the science community. All of you guys are like this. All of you. I had a lot of friends like you, even I was in the community. And this is a lack of information of history, basic history, blindly accepting everything and coming to this point. Take care of yourself, bro. Take care of yourself.
Yeah, I'll look into it some more. It's been a while since I've looked at some of these, but yeah, I think that's a good idea.
Want to know more about it? Let me just tell you, this experiment, this era of physics, 1905, I think it was around. Oh, sorry, it was 1880, 1898. I don't exactly remember the date, but that was the era which the physics literally changed. Now, if you talk with some conspiracy theorists about what happened back in time, they will always mention this date or this era, that the physics has changed dramatically, because before all this experiment, all our fathers in physics, like Jordan Maxwell, or Lawrence, or even a lot of them, I forgot their names right now. You got Ampere, you got a lot of them, like you got Lenz. If you check them out, my brother, all of them believe in the luminiferous ether. But you have to respect these guys, because these guys are responsible for all the things that we're working with them. The electromagnetic, our phones. You know what I'm saying? These are the fathers of electron, and we cannot dismiss what they have said and said, okay, you guys were wrong, and everything that Einstein said is true, and blah, blah, blah. As I said, it's very deep, and it's all about history and conspiracy, and it's not all about physics and formula. It's blended together. You know what I'm saying? So it's very interesting.
Yeah.
If you like physics, if you want to work on physics, I suggest you to go back in time a little bit. It's more interested.
Yeah, the history of physics is really interesting. I just whenever I think of that, like they did all believe in the ether, but it was an obvious thing to believe in at the time without any experiments being done on it. And yeah, a lot of physicists were very adamant about the ether, and there wasn't like a huge shift all at once, actually. It took quite a bit of time for people to fully accept it. And there were still some people that were very tightly clutching to it. And that I think a lot of the time has to do more with those personalities. They were very intelligent, especially Maxwell, Lorentz, Lenz. They were all, I mean, they were Henry. Like they were all quite intelligent, especially to come up with these theories and laws. But ultimately, I think they were mostly constrained by their lack of knowledge and lack of experiments in a lot of cases. They had great ideas, but just being a founder of something doesn't mean that everything you thought of was right. There are plenty of people who have had great ideas, but then turned around and were very wrong about certain things. I don't think that they should be completely ignored, of course. But I also don't think that we should give them unnecessary credit for things that we've already shown to be superfluous, right? That's not I think either side is unfair. I think it's good to look at it, but not to be too I think the conspiratorial part of it is kind of a turnoff, because conspiracies are sure, they're everywhere, but in this case, these are things that we can verify now. We can verify these things. That's the beauty of physics, is that you can verify things. You can do experiment, and if your theory doesn't match with experiment, then it's wrong. And if experiment, I mean, we have done interferometry experiments, many interferometry experiments that they'll verify the results of the Michelson-Morley experiment.
You didn't understand what I said. It's not about the instruments or the interferometers can detect the ether. It's about the presumption, my brother. Why this is so interesting for me, that no matter how many times go back to the same point, it's not about how advanced the instruments were. It's not about how much they worked on it. It's about the presumption that is behind that experiment.
Yeah, that the Earth is moving.
Yeah. So hold on. So the drag of ether, would it be the drag of ether wasn't detected by those interferometers 100 years ago, and we know that even today, the advanced interferometers cannot still detect the drag of ether. That is for sure. But you're missing the point. As I said, this is because you're presuming that the Earth is moving into space.
I mean,
This is the point this is so important. I want you to just focus on this very, very first step before you go to the experiment by itself, before you start working on the experiment. You need to know what is your presumptions. You need to know what you're presuming before you go doing your experiment. And that is the problem that we have.
Yeah, I think
Go talk with ChatGPT. Go talk with ChatGPT. Discuss with ChatGPT about this point that I told you. Okay,
sorry, Kasra. You know you presume the opposite, but then ignore the actual science that has been done and proven. Like, I don't understand the argument you're trying to get MackingCheese on. Like, honestly.
You're assuming that the Earth is stationary rather than moving. You're making the exact.
Yeah, sorry, Macking. Like, he's having a go at you for presuming one thing, and yeah, you are kind of, but it's based on like an experiment that's been done. Whereas he presumes the opposite, ignores the actual science, and then goes from there. And then that's his argument. Like, I have a huge problem with that.
Yeah, I think like, so yeah, I assumed that the Earth was in motion. But we assume a lot of things naturally, and I think that if we have to analyze every specific assumption, I think we should only really analyze those that seem reasonable. And maybe the Earth's motion is I mean, it's a foundational assumption here that is important in the context of the experiment.
No, it's not. It's not a foundation. It's not.
No, I mean foundational as in it's important.
No, it's not foundation. It has become a foundation in our brain in the last 100 years.
You're misunderstanding. I just mean that it's important to the context. I just mean that in the context of this problem, it's important.
Hey, Kasra, do you use Wi-Fi? Do you use Wi-Fi in your home network or on your mobile phone or anything?
Yeah, of course, but it has to do with the topic.
Well, I mean, you can't see it working, and it was discovered by science. But why should you believe in it? It should be, I don't know, fucking magic.
It's not a direct measurement. Let me just, because you're not probably don't.
Oh, really? It's not a direct measurement. Yeah, okay.
It's not of course, it's not a direct measurement. It's based on some presumption, and I don't agree that we need to presume a lot of things and then do the experiment.
Your Wi-Fi, and the protocols around it work on presumptions.
You're just gaslighting the argument. We're not talking about Wi-Fi and the technology. We were working the foundation of our physics.
You're gaslighting why you don't believe in older science just to try and justify your position.
No, I don't believe.
You are,
I
full of shit, dude. You are full of shit.
I don't believe in anything. I have to make sure myself. I don't believe.
I don't believe in anything.
It's not a religion, bro. If it's because you got treated like a religion,
if you don't believe in anything, you should just like turn off all your electronics right now, because every bit of science that has been done, every bit of science that has been done to try and prove that all of that stuff works and how it works and whatever, you shouldn't believe in. Go back outside, grab your fucking plow, because you know that digs dirt. Go for it.
Become like a farmer. Okay. Yeah. So obviously, it's important to us that we should know that the Earth is moving around the sun. Sure. In general relativity, this kind of motion is relative, one might say.
Why is it important? Why is it important to believe that the Earth is moving around the sun? Why?
No, well, he hasn't addressed anything. He hasn't addressed anything that I've said. He hasn't addressed anything that I said to him, and he's just full of shit.
No, I understand what you're saying. You say that 100, you have to accept 100 things that the science is telling us. No, I'm not that type of person. I believe in 80% of the science. 20% is wrong. And this is the 20%. The 20% is the sun, the Earth hasn't directly measured to be moved. And if it wasn't very, very something interesting, or it wasn't so important, then why they came up with that very beautiful experiment, and an experiment that they gave Nobel Prize to them. So it was so important for humanity to make sure itself that whether the Earth is moving or not. and they couldn't measure it directly. And today, you guys are saying that, oh, it's not important. We just have to accept everything because the science have made Wi-Fi for you. Just because the science made car for you, you have to accept everything that is bad. No, this is so retarded. I'm sorry. We're not like that. Flat earthers are like that. I'm not a flat earther by myself anymore. But people,
because you say it's retarded. It's retarded.
Well, I think the two things, and one of them is that if they have developed all of these advanced technology and all of these things, then there has to be some merit to what they're talking about, and I think that's one reason to accept a lot of the things. I don't think you should accept everything. I don't think anyone should accept everything at face value. But there are certain things where
no, you can be reasonable about it though.
Yeah, you got to be reasonable, and I think in this case, if you don't believe that the Earth moves, then at least what you'd have is something like there is technically an equivalent, what we would generally call an equivalent frame where you're in the Earth's rest frame, and so everything else is kind of moving with respect to the Earth. But this isn't an inertial frame, so it's actually not Lorentz invariant, and so it's not equivalent to every other frame. And so we should actually be able to tell that the Earth is moving, and we do measure it. We measure its relative motion with respect to other bodies. The reason why I don't believe that this is equivalent has more to do with the physical motivation for that. So physically, if the Earth was stationary, then do you believe that the Earth is rotating, like it's stationary and rotating?
Earth was rotating.
Seriously, like one of the key questions that flat earthers can never answer is why does the sun rise and set? Like they never answer it. They use some sort of
it's spinning on its axis, right? Oh, I don't think he left. I think he's having problems with his mic or his audio or something.
Okay,
but the Earth is it's spinning on its axis, and if you don't believe that, and you mean that, so do you think the Earth is spinning on its axis? I guess. Kasra.
Sorry, I had a phone call. I didn't understand. What did you say? What did you ask?
Do you think the Earth is spinning on its axis, or do you think it's completely stationary and that everything else is moving around it?
Well, okay, so that's a good question. You're saying, do you think? You're not saying that. Do you believe? Because in the first you said that. Do you believe the Earth? No, I don't believe in anything. I want to make sure. So, as I said, personally, I haven't proven myself that the Earth is moving. Right? I couldn't justify myself that Earth is moving because I don't want to get into my what I know. But the thing is that what I'm sure is that the airplanes, they don't count the speed of the Earth inside their navigation. This is for
sorry,
sure.
hang on. No, we need to address the way you frame. Sorry, we need to address the way you frame an argument. I don't know exactly how my fucking car works, but I know I can go outside right now, turn it on, and it will drive me somewhere. Right? So you're just saying, well, because I don't personally know how it works, well, then it's invalid. Like,
you don't know. But
do you know how stupid you sound?
No, you don't know. But I know a lot of people, at least in this room, that they done a lot of years research on this. That the Earth doesn't move, like at least airplanes, they don't count the spin of the Earth with even the ballistic missile, nothing at all. And the frame that we use is a stationary
because angular momentum is conserved. It's because angular momentum is conserved that is possible.
Thank you.
Yeah, it's like, why doesn't when the helicopter takes off, it doesn't fly off at 1,400 kilometers an hour? Like,
yeah. So that's
the helicopter goes up. Yeah, sorry, I interrupted you.
That's specifically because we're moving with the atmosphere. So we carry the angular momentum of the Earth, and so planes are always moving with respect to that.
So you're saying the atmosphere is rigidly moving with the Earth. This is the presumption again that you have to have in your mind. to make yourself sure the Earth is moving. You have to believe that the surface is, if the surface is moving, let's say on the equator is moving 100 kilometers per hour, 1,000 kilometers per hour, 1,000 miles per hour.
1,000 miles an hour.
You're assuming, so you're assuming the atmosphere above the surface is moving exactly with the same speed. Because if it wouldn't move the same speed, my brother, no, even it's no, it has to be exact. Because
well, then, dude, you should not be able to talk on Wi-Fi because your Wi-Fi waves should just fucking move away. They should just escape to space. There's nothing holding them down.
I just want to have a rational conversation with Cheese, and that's all it is.
Yeah. Okay. Well, I think I know. I think I know why it's kind of hard to accept that the atmosphere would be moving with the Earth like that, because we're used to things like the Earth. You know, we're used to thinking of the Earth as like spinning, and then maybe just the atmosphere is free floating kind of around it. But the atmosphere. Remember, the atmosphere wasn't always here, right? At least in terms of how we believe that the Earth is formed. So if you can take that for granted, the way that the Earth formed,
there's no way
right?
Kasra is going to take that for granted. No
Yeah,
way.
exactly.
Well, I think it's okay.
Good point.
Because fucking God did it,
I don't know.
I
don't know
think
why you
that
guys go back
if you want to have a good faith
and say that we have
conversation,
to.
yeah, I think that it's you. I think that in order to have a good faith conversation, then you must at least hear out what our argument is, right? So I guess what we're saying is that in the Earth's formation, in our conception of cosmological history, the Earth formed with this angular momentum. The Earth formed spinning. And so, regardless of how that happened, the Earth formed spinning, and then the atmosphere on this already spinning Earth basically arose already on the Earth. Not like the Earth formed with an already prepared atmosphere, but over billions of years, the Earth is still rotating, and these you have an atmosphere that starts forming due to whatever geological processes, whatever comets are hitting, all of these things, and because of specifically gravity, they're able to be kept in this kind of gradient, and they conserve that kind of angular momentum and rotate around with the Earth near the surface. So the air around the Earth maintains, and the atmosphere around it maintains the angular momentum of the Earth, and it always moves relative to the surface because of that. In fact, if we assume that, then I see no reason that the air or the Earth or anything taking off from the Earth should suddenly have a kind of a shift in angular momentum, specifically because there are no fixed frames, right?
Yeah. So can I ask a question? So you're saying that the atmosphere will maintain its angular velocity along with the Earth. Now, until what height it will preserve its angular velocity? Let's say you have an airplane that it's about 20,000 feet, 30,000 feet. So based on what you say, you think that in 10 kilometers, which will be 30,000 feet, which airplanes move on, that on that area, the whole atmosphere is moving along with the Earth with the same angular velocity. This is your claim, okay? Is that correct? Okay.
Yeah, it should be moving with the same angular
is that correct?
Momentum at every level.
So you're saying that. So you're saying that the air around that airplane that is flying around 30,000 feet, that air is moving with the same velocity or the same angular velocity of the Earth, right? Is that right?
Yes. The angular velocity.
So is the fucking plane, you dickhead.
I mean, that is true.
Here's the kicker. You're simply wrong. Because if you study fluid mechanics, and I'm going to give you a very short terminology.
The viscosity of the Earth's atmosphere is not enough to actually produce that large of a viscous force.
Let me just. I was quiet for 5 minutes. please don't intrude. Let me just continue what I was trying to tell. This is so important for you. There is a condition in fluid mechanics called no slip condition. No slip condition tells us in fluid mechanics that if you would have a stationary air, and if you would have a plate, and if you move the plate inside the stationary air, the air exactly on the surface of the plate would have the same velocity that the plate has. Or let's say you have a stationary plate and the air is moving with a velocity over the plate, right? Again, the velocity of the air exactly on the surface of the plate will be the same as the upper stream that is coming.
Are you talking about Coet flow?
No, I'm talking about the boundary layers of the fluids. Any fluid that passes or any solid object, there would be some layers that it would have the same velocity as that object has, but the upper stream would have a different velocity. So let's say, as I say, let's say you have
that's dependent on the viscosity of the fluid.
Exactly.
But
exactly.
air is not viscous enough for that. You can calculate this actually. You can calculate exactly.
You're walking with me, okay? We calculate that. We calculate as a flat earther, as somebody who worked 10 years on flat Earth. This is my words to you. We calculate that. We had the viscosity of the air. We put it in the formula. We found the tear shear, the force shear exerting on the surface of the surface of the Earth, and by that formula, which as I told you, go study about the formula and no slip condition, you can know that on what height the velocity would have started declining or started reducing. Let's say if Earth is moving with 1,000 miles per hour on the equator, based on this condition and this principle in fluid mechanics, we can assume that the lower layers of the atmosphere would have had the same velocity as Earth has because of the viscosity. But as you move,
I might check this.
Yeah, hold on. Yeah, but
I was actually just doing this problem earlier today, Coet flow. It was on a coaxial cylinder, but I think it's the same principle. Yeah, it's the force is something like the viscosity terms times height. What is it? Times the well, it depends on the actual surface area of the object, and it's the gradient of the fluid velocity with respect to distance from the actual velocity.
Yeah.
Exactly. Yeah. I was working on that. Hold on.
So let me just help you with this one, because we're going to use this on the flat Earth conversation here. So I do agree that so if Earth is moving with that velocity on the equator, the surface is moving, right? So the air above that surface would have moved with the same velocity based on this condition that we spoke.
The surface and the air are not moving relative to each other. So
no,
it's
exactly.
Not
exactly. They have the same velocity. But as you move up, when you go up, when you increase your height, the profile of the velocity decreases. Why? Because of the viscosity. Do you agree?
I don't. Let's see. No. Because the fluid and the object are actually moving at the same velocity.
Yeah, but
there's no relative velocity between them.
No, but
they're both stationary in their rest frame.
Kilometers is 1,000 kilometers. Thickness is about 1,000 kilometers. The atmosphere thickness is about 1,000 kilometers. Based on this thing that we know both together, my friend, we know that at least, let's say, the first 10 kilometers, at least 1 kilometer, I don't know, but this is the thing that we have to work on it. It would have moved along with the Earth. But the higher layers of the atmosphere would not move along with the Earth. This is based on what we spoke right now. No slip condition and the flow that you said that has to be with
that's only so you're assuming that they're moving relative to each other. That does actually assume that it's moving relative to the fluid, and that's not happening here.
Are we still talking about airplanes? Like, I just need some context.
No. This is a bit more technical, but you're assuming that they're moving with respect to each other, and Coet flow is specifically when you can assume that. But if they're moving exactly the same, then there would be no Coet flow in that case.
If they move with the same exact velocity, but we know that as you move up, that velocity decreases. You have a profile for your velocity. You said it right now.
No, what I'm saying is that Coet flow is within the paradigm of a stationary fluid and a plate moving across it. There has to be some sort of relative motion, but there is no relative motion here. Therefore, the velocity is 0. There is no shear.
Only
There
for
is
the
no force.
layers that is attached to that plate, okay? But the layers above the upstream, they would not move. If you would have a stationary air, and if you move your plate inside that stationary air, only the layer that is close to the plate would have moved with the plate.
Yes, what I'm saying is that the plate is not moving with respect to the air. I think you're fundamentally. I think there's a small misunderstanding here, which is the fact that
say it again. What did you say? What did you say? Say it again.
You're assuming that the plate is not moving with the air in this example. The Earth's surface is not moving with respect to the air. They are at the same velocity. Their relative velocity is 0. So therefore, there should be no co-ed flow. This is fundamentally why you wouldn't see that.
Hold on. What about the surface? The surface has a friction compared to the other higher layers of the atmosphere. So within the million years, we're talking about the formation of the Earth. Okay, between two layers. No, okay, between two close layers. But if you compared the velocity of the surface with the velocity of the air, like 1,000 kilometers above the Earth, they would be different. Now, this is the crazy thing that you guys are saying.
Should still be the same thing.
Well, this is magic. You're saying that the whole atmosphere, even the top layers, which is 1,000 kilometers above the Earth, is moving with the same speed. This is crazy.
Only the same angular velocity.
No, I told you, even based on no slip condition, it's impossible. The viscosity wouldn't allow those higher layers to move with the Earth. Only the lower layers would have moved with the Earth. We have a formula for that. I can do it for you if you want. You can do it by yourself as a homework.
That formula is derived from the fact that you need to conserve energy. But in this case, there's no way for us for the energy to leak out necessarily. It's a conserved system. There's no dissipative. I mean, there's no non-negligible dissipative force in here.
So you're saying there's no friction between the air and the surface? Hold on. So you're saying that there's no friction between the air and the surface of the Earth since the beginning of the formation? This is what you're claiming.
Maybe there was at the beginning of the formation, but that doesn't stack up.
When you're saying that it's a conservative environment, you're saying that there's no in and out. You're saying there's no loss in energy. Everything is kept and preserved and maintained since the beginning. Now, if this is the case, what you're claiming, you're saying that we don't have any loss of energy due to the friction of the surface and the air, and because they've been conserved all these years.
This is crazy. It is a conservative system. Perhaps in the past it wasn't, but you can have systems that
since the beginning you can. Oh my God.
No, that's not what conservation means. That means that in this specific frame.
I know trying to run away from trying to have a solution or so, but just think about it.
Also, what does between the friction of the surface and the air mean? Explain that.
No. Hold on.
I think he means at the beginning of the Earth's formation.
Trying to find what means. Think about it again. No, some of the things doesn't make sense in the globe model. This is the whole point. It's very complicated. You have to bring in a lot of theories and a lot of things right now to make things work out. Like saying that the angular velocity of the top layers of the atmosphere, even those molecules that are 1,000 kilometers above the Earth, they are exactly moving with the surface of the Earth. This is magic.
No, it's conservation of angular momentum. It follows directly from conservation of angular momentum, actually.
How do you explain it?
Well, I mean, I don't think he believes it.
No, I believe in angular momentum. So angular momentum, basically, you guys are saying that, for example, if there's no friction, if there's no conservative force, the thing would have moved forever. This is called whatever you were talking. You're saying that, or if it's rotating.
That's linear momentum. It just means that angular momentum doesn't change.
Yeah, the angular momentum doesn't change. The velocity doesn't change. Everything is conserved. There's no loss in energy. There's no entropy. You know what I'm saying? So it's very neat and clean. I don't want to get into the entropy right now.
There will be entropy.
But the point is, what I'm trying to say is that the model that you guys presume, it's way more harder than just believing that things are stationary, nothing is moving. Because if you think that nothing is moving, everything will work out. Because you don't need to come up with angular velocity theory to just say that there's no relative velocity. Yes, there's no relative velocity because nothing is moving. Everything is stationary.
The issue is that if everything's stationary, then physically, there are a lot of unphysical things that will happen. For example, if everything is stationary, then that means that the entire universe has to rotate around us, and that is completely unphysical.
Okay. But
Right.
I don't
And that's one of the main reasons why we wouldn't believe that. Just it's completely unphysical.
You say there's no friction between the atmosphere, the air, the wind, and the hard surface and the oceans, right?
Specifically, the atmosphere, locally, the atmosphere and the surface of the Earth are relatively at rest, so there should be no friction.
Yeah, but as soon as you have a change in direction of the atmosphere, the wind, the cyclones, the tornadoes, we have another thing called Coriolis. There's a whole bunch of stuff there with, as soon as you have a change in direction, that's when you're going to cause friction. And there's like it's like a fairy tale, bro.
I know what you're saying. Those are internal forces. So internal forces within a system won't change the overall net force. So I know what you're saying, but these are things that are happening already within the system that has that angular momentum. So while yes, there are winds that blow kind of left and right and whatnot, an object cannot force itself. It can't self-interact in that way classically. So that's just something that's happening relative to the surface of the Earth. It's not going to be.
You know why you're wrong?
How can I say
tell you why you're wrong.
I'll tell you something like the difference, like a lot of ballers, they explain, well, it's like a river and you have currents in the river. Guess what, man? The river is moving. That's the difference, right? That's why you can say, well, it's got currents and it's just like the atmosphere, it has currents. No, yeah, but the river's actually provably, demonstrably moving, right? That's the difference. And that's what's in contention here.
Sorry, the river compared to what?
But the river's moving with respect to the Earth,
though. Currents, and you've got the oceans, which are tidal, and then you've got the currents, right? And you've got different oceans mixing together as well, which are all under the influence of the tidal from the moon. But what we're trying to say is that you're going to have friction because you've got all these different attributes of the atmosphere. It's not just one thing. The atmosphere is made up a whole bunch of different things, man.
Yeah, I thought you were talking about the atmosphere.
The atmosphere does move around, and there is wind and whatnot with respect to the Earth. Ultimately, on average, all of that behavior is at least somewhat. I'm no meteorologist, but I would expect it to be at least random and likely on the order of negligibility. But the really important thing is that in comparison to the velocity and angular momentum that's imparted by the Earth's rotation from conservation of angular momentum, the movement of unless you have like 100-mile-an-hour winds and things like that, the movement of the wind is going to be negligible compared to the actual linear velocity.
This is all done by pure speculation and calculation, right? There's never been a demonstration.
I mean, it's explained. It's explained very well by the theory.
Look, there's never been a scaled down version in practical reality, tangible reality.
There doesn't need to be one.
Well, there does. That's the problem.
If you don't do that,
and you're just basing it on like pretty much fairy tales, man. I tell you.
I mean,
it is a fairy tale. Why is it a fairy tale? Because hold on. You're saying that the initial velocity of any airplane or any aircraft, once it's liftoff, that initial angular velocity that it gains from the Earth, that would have preserved all the way up to the sky, and it will always maintain that initial angular velocity with itself in order to always move.
You kind of cut out there at the end. Sorry. But it would.
Magic.
It would preserve angular velocity because there's no force acting on it to change its angular velocity.
Drive 100 km an hour in a car and throw a tennis ball up, and see if it maintains its angular velocity.
Yeah, I mean the thing is that it's moving with the atmosphere.
You guys are dealing with a closed system. If you open up the window in that car, everything
and also
changes.
unlike a tennis ball, a plane has fucking energy propelling it.
Are you imagining that the atmosphere is stationary and the Earth is moving, and then that the plane has to basically?
I'm saying that based on what you're saying. You're saying that you're saying that when a helicopter goes up, it has an angular velocity, an initial angular velocity, right? You believe in that, right? Okay. Now you're saying that no matter how it maneuvers up in the sky, no matter where it goes, no matter how long it stays up there, it would have always maintained this initial angular velocity because they're all conservative force up there. You're saying that the friction of the atmosphere with the air helicopter is a conservative. Well, this is not true. You're saying that like even if the helicopter goes in the different layers of the atmosphere.
Well, no. Well, not perfectly.
If it's going straight up, then...
But a helicopter has a fucking engine, right?
I mean,
no. Let's say a balloon. Let's say a balloon. Just fuck the engine. Let's say a balloon. You're saying that when a balloon goes up there, the air doesn't change its initial velocity. Well, this is against physics. This is against all the things that I've learned from the fucking
school. No, but it changes which way it goes.
The wind itself might blow the balloon around or something. The wind might blow the balloon around or something. But I mean, if I didn't imagine that we were going to be pedantic like that. We're talking about the atmosphere of the Earth and planes and whatnot.
You're saying that when a balloon goes up there, and when it comes back exactly to the same point, let's say a very clear day without any wind, no disturbances, you're saying that the reason that the balloon comes back exactly to the same spot is because the atmosphere is moving with the Earth.
Yeah, it's a conservative system. Yeah.
Yeah, okay, so it's not irrelevant what I said about the balloon. So this is a crazy part that you're.
I gotta say, for that balloon to come back to the exact same spot, it must have been really perfect conditions.
Yeah, let's say perfect condition. We're engineers, which is what you do in science. We can presume that we have a clear sight. We just rule out all the disturbances. We only will keep the parameters that we need in the system. So one is the spin of the Earth, one is the height, and some other stuff. Now, if we do that, based on your claim, you're saying that when a balloon goes up, like some of them go high, like 100,000 feet, 120,000 feet, you can see the black sky. And you're saying that once it's go up there,
to go up 120,000 feet. No, what's the balloon full of though to make it go that high?
I don't think that's important. It's just a thought experiment.
This is not. You're gaslighting.
Sure.
This is not.
Okay.
You're gaslighting.
Okay. No, sorry. I'm sorry.
Yeah. So when you come, so you're saying that when that balloon goes up there, and when it comes back down, the reason that roughly comes back to the same spot. Let's include some disturbances for better experiment. You're saying that when it comes roughly the same spot, the reason that it comes exactly the same spot is because that atmosphere up there, like that the 100,000 feet, that altitude. You're saying that atmosphere, those molecules. This is literally what you're saying. You're saying the molecules have the same angular velocity. And the balloon itself has preserved all that initial angular velocity that it had in the beginning, and it kept it up there. No matter how many these layers have changed, it just all kept it up there, and it didn't change. But this is, as I said, this is against physics.
The angular. That's just conservation of angular momentum. I don't know what you want me to say.
I'm
you have friction. Hold on, you have a friction. You have a friction.
But hang on,
I'm
no
scientist. To the direction of motion. I mean,
I'm no scientist.
No. You cannot include when you have a conservative system. You cannot include any unconservative force. You need to understand this.
I mean,
in reality, we have friction and friction are unconservative forces, and they will change the system. You will come out of your first situation that you had, that initial
But
velocity you
dimensionally,
had.
it's only dissipative in the r direction. It's only dissipative in the radial direction because the balloon, with respect to the Earth, is only moving radially up. I mean, it's moving upwards, right? So it's moving radially outward. So it wouldn't actually have anything to do with its angular. It wouldn't impart any torque at all because it's completely orthogonal to the angular velocity. There would be no change. Does
No,
that make
there's no
sense?
torque. There's no torque. I'm not saying that there's no torque. You have just angular velocity. You have omega. You have that omega with the omega zero, that Earth. What is the omega zero of the Earth? It's about, I think it's about 10 to the power minus 5 radian per second.
It's not
Yeah,
super
something like
important.
that. Now, you're saying that it is preserving this omega all the way up there. And it just preserves, and you're saying that no matter how long it stays up there, let's say that balloon can stay like 4 days up there, right? You're still saying that this is a whole conservative environment and everything is conservative. It's not. This is not how we define a conservative system in physics.
It's only conserve. I mean, the only quantity that we're actually interested in here is the angular momentum, and so it's going to be conservative in the sense that it's not moving with respect. It's not moving in the angular direction. It just isn't with respect to the atmosphere.
Let me tell you what is a conservative angular momentum. When you launch a satellite into a space, once that satellite injects into an orbit, it will start to tumble. That tumble has 3 components: omega y, omega z, omega x in 3 direction, right? And you want to detumble it with your angular control system that you have over there. Now, so that
that's cool. You believe in satellites, at least.
The reason that it tumbles is because it's moving with.
Now, if you wouldn't have any system to tumble that satellite, because of there's no air up there, and this is where I'm trying to tell you that where is a real conservative environment. When that satellite is like very high orbits, right? Like where you have even higher than the ISS, right? Like geosynchronous satellites, right? Geosynchronous satellites, 4,000 kilometers. Now, on those environments, literally, there is no air, or even if it would be very, very, very small, right?
Very few air.
In that environment, if I tumble a satellite, I know it would always tumble forever, and there is no conservative force to slow down that satellite, because my satellite is within a conservative environment. This is how we can assume that something is in a conservative environment.
Wait. Satellites have to battle gravity.
No, we're not talking about gravity here. Let's leave the gravity. Hold on.
Do you understand that the balloon in this situation is not the satellite is orbiting? It's moving in the angular direction, so it has to move and specifically through the air in such a way that it changes its angular momentum. But in this case, the balloon is moving purely vertically up, which means that it's not affecting its angular momentum at all.
The satellite can only change its angular momentum with the device that is had inside, like a angular, like a momentum wheel,
assuming that it's a conservative environment. But what I'm saying is that the balloon.
Anyway. Yeah. So hold on. So you're comparing 2 things together to be the same thing. You're saying that a satellite in space, which is in a conservative environment, is the same thing. The balloon goes up to the 30,000 feet up. Yes,
I'm not saying that.
I'm sorry.
No. I think you misunderstood me. What I'm saying is that they're different specifically because the satellite is moving in the angular direction when it's orbiting. The balloon is moving purely in the radial direction. They're actually opposites. And I don't even think they're really good to compare the two, because the balloon is moving in the radial direction, so its angular momentum will not be changing because it's not moving with respect to the atmosphere, which would actually provide some sort of drag force and change its angular momentum. But the drag force that's being applied on it is in the direction of motion, which is vertical, which has nothing to do with its angular momentum, which it still has from its initial
angular momentum.
Or
you're saying that there's no drag force?
There is a drag force, just not in the direction of angular motion, which means the angular momentum would not change. Angular
No, I'm
momentum
not
is
talking about the
conserved.
radial. I'm not talking. Yeah. I'm talking about I'm not talking about the radial direction. I'm talking about the rotation direction. So you're saying there's no friction, there's no unconserved force on the radial direction. Sorry, on the rotation direction.
If we're moving purely vertically, if the balloon is moving up and down vertically,
No, let's
in
say
terms of
the balloon is up there. Let's say the balloon has arrived where it wants. It's 100,000
okay,
feet, staying up there for one night. Now, what are you saying here? You're saying that there's no friction.
No, because
Yeah,
it's not
and
moving
like
with respect to the atmosphere.
this is where he's definitely wrong, right? Because it's a globe. It's not just a flat linear motion. We've got the Earth is moving 400 meters per second at the equator, and on that latitude compared to other latitudes, you've got different tangential motion. You're going to have friction. You've got different vectors going on, and science does say that there is a minimum amount of friction that's
No,
admitted to.
I understand the physical situation, and there wouldn't be friction specifically because the object is not
And drag.
moving with respect to the atmosphere. So there is nothing to do friction on it because it is not moving with respect to the atmosphere. It is specifically stationary within the atmosphere, within the Earth's
You can
rotational
keep
frame.
asserting that as much as you like, but there's no evidence for that. It's just the
That's what we're
assumption that you
considering.
don't need a container to hold in the atmosphere. And
But
because you've
that's
got that
literally what
assumption,
we're assuming that that's the case. What do you mean there's no evidence for it? We're
because of
assuming that
you,
this
yeah,
is
I
the
know,
case.
because of this assumption, that's why you can assert all of these things, because you've got
Well,
that underlying assumption.
that's
And
the
and it's
point,
only
though.
assumption. No, but
No,
it's
even if
only
they
an assumption
underline that
because all
assumption
evidence
doesn't work.
shows that gas pressure needs containment, dude.
That's completely beside the
Even
point.
underlying that, even underlying this thing, still they cannot explain it. This is my point. I'm trying to tell them.
I've
Even if they
been trying
presume
to
that the Earth is
explain it to
moving,
you for
no,
the
no,
better part of an
still they
hour.
cannot
I don't know what
explain
you
it.
want me to do. I I feel bad now
I
because
heard
I feel
you.
like I haven't really communicated it well. But
No, I think
look,
like dude, like mac and cheese. I think your theory is all correct. It is all correct, but it's all based on an assumption. Therefore, it's fallacious. It's fallacious, and it's begging the question.
I haven't been here very long, but I'm pretty sure they were talking about like a hypothetical perfect system. Like we're talking about what happens physically in reality, that would be kind of different.
Yeah, I mean the scenario was really I think Kasra was asking why when when you have the Earth rotating, why when a plane takes off, yeah, I suppose how it has that sort of angular momentum, and how it's not slowed down by the atmosphere. Well, I mean, within the Earth's reference frame, the plane has to be slowed down by the Earth's atmosphere because it's moving with respect to the Earth's atmosphere. We were talking about a balloon just now, and if the balloon moves vertically upward through the atmosphere and it doesn't move with respect to the atmosphere, then that means that any angular momentum that it would have wouldn't be able to change since there is no drag force being applied in the angular direction. Therefore, angular momentum is conserved, and it really shouldn't change angular velocity at all. There's no
Dude, you're
reason to think that it
separating the
should.
Oh, hold on.
airplane
Okay, cool,
from
cool.
the Earth.
What about?
Like these are two solid things. You're separating a mountain and an airplane. You're making them like as if they're two different things in the atmosphere. And they're not. They're solid things moving together or apart from the atmosphere.
I don't think I quite follow what you're saying.
You equated a balloon and a mountain.
No. If he's saying that since the formation of
You
the Earth,
say
this is
that
what
there's
he's saying
drag
since
when
the
an
beginning.
airplane flies around. You admit to that. But what's the difference between an airplane flying around in the atmosphere or a balloon or a stick or a bird or a butterfly and a mountain? Just because the mountain's actually fixed to where you stand, it doesn't make any difference. It's all within the atmosphere. And you just admitted there is drag, there is friction. It's like
Well, that is the difference.
contradicting information, dude.
The difference is that the
The
mountain
mountain.
isn't moving. It can't move with
So what about the
respect to
friction? I
the
don't
Earth's
understand. What about
surface.
the ground? What about the ground? You have dismissed the ground friction. And you're in this theory that you came up like since the formation of the Earth, since the beginning, everything was moving along together. Well, I got your point. That was cool, by the way. You say that it wasn't like, but you're wrong. You know why? Because the atmosphere was made after the crust and the surface of the Earth. So if the Earth was moving with a specific velocity, and then the atmosphere, came out and made up, then that atmosphere gradually should have started moving with the Earth because due to the friction. And right now, you're saying that friction is nowhere, and we don't have friction. Everything is moving solidly. This is the part that we don't get. It doesn't really make sense. Even based on the theory that you said, the gradual formation of the Earth and its atmosphere, that it was all together at the same time.
I'll be
moving
honest.
together.
I can't say that I fully understand the theory of the formation of the Earth's atmosphere and the Earth itself. This is
the atmosphere was made after the crust. This is for sure. This is 100%.
Yeah.
The Earth was without the atmosphere in the first stage. Okay, so if this is the case, we have to be realistic. If this is the case, if the Earth had to move that angular velocity since the beginning, therefore this atmosphere should have started to build up its velocity as time passes on, right? And then eventually, based on what you're saying, that the velocity the velocity reaches the velocity of the surface of the Earth, the velocity of the atmosphere. And now, because of this thing happened, we don't see any relative velocity because everything is rigidly moving together. But this is really,
but why should that be the assumption?
I mean, yeah,
your assumption.
Like,
this is
think of.
What you're saying.
I also don't know exactly how the. No. I also don't know exactly how the atmosphere was formed, but from my understanding, it either was from like ice that came in from comets that then evaporated,
so how do you
or processes from the Earth
together
itself that puffed out some sort of atmospheric elements. But all of those would have been processes on the Earth, so they would have inherited the momentum from the Earth in the first place.
I think in any case, they would have that angular momentum. What were you trying to say, Kasra?
Yeah, that's exactly. You said it right. You're saying that the moment that let's say those gases burst out the surface of the Earth, the moment they come to the atmosphere, or let's say to the vacuum, because it was a vacuum in the first place, it wasn't the atmosphere, they will start to move with the Earth. Right? This is how it really looks like, based on what you're saying, that during the formation, that everything gradually started, everything, the atmosphere. Now, even based on this theory, now this is my point. I'm trying to be within your narrative. We're not talking about, even based on this thing that we believe into it in mainstream science, still the friction between the surface of the Earth and the atmosphere would have existed, and that would have caused some differences. And those differences should have. Sorry?
Why would there be friction between the atmosphere and the Earth if they're both stationary with respect to each other? The friction should be based on the velocity of the fluid with respect to the surface, which there is none.
Because when it goes up, let's say. You're talking about what? Sorry.
You're talking about Coet flow. The shear with the plate. This is Coet flow, and it's when you have a viscous fluid, and it's specifically not. I mean, if there's velocity between them, then you're going to have Coet flow, and you're going to have viscosity, and you're obviously going to have viscosity, but you're going to have friction. Without velocity, relative velocity between the two of them, there is no force, there is no friction, there is no Coet flow.
So you're saying that when we pour sugar in our tea, when we stir our tea with a spoon, we can see that the fluid close to the pivot point, which is your spoon, would have moved faster than the tea that is at the edge of your cup. This is because of the viscosity.
Because there's relative motion between the fluid.
You're completely missing this out in your reality.
No, but what I'm saying is that there is no relative motion between the atmosphere and the surface of the Earth, so there should be no friction. That's what I'm saying.
So you can read that. So this is like, just come to this example of the spoon and the tea. When you move the spoon, that's your Earth, right? Even if this, so you're saying that this, let's say the tea comes out of the spoon, you're saying like the Earth. But the tea is the atmosphere, and the spoon is the Earth.
But the tea is stationary when you're stirring it. And then the spoon is moving, so there's relative velocity between them. I'm saying there is no relative velocity.
Even if the tea wasn't stationary, let's say the tea would have come out of the spoon. Let's say there's some holes in the spoon. Let's say we had made it thick spoon, some holes in the spoon, and the tea would have poured out the spoon once we start, rotating the spoon. Okay, this is what you're saying. Now, if you do
whenever
that,
you're rotating the spoon, it's going to have a relative velocity with
it's
respect
going to
to
have the
the.
same exactly. Yeah, exactly. They're going to have the
It
same
is
angular
just
velocity.
I
But
don't know
the
if the
moment
tea
that
and
you
the
come
spoon
out
is
of
example is wrong. Your
I
example
think the
in
example
this
is actually
example,
very
if you're going
difficult
with,
this is
to.
your world, this is your sphere,
it
this is
just
your
doesn't match. No, our reality would say that the cup is the earth and the tea is the atmosphere. Like what
I
you're
think that's
introducing as a
also a good.
spoon would be something else that's actually moving the atmosphere.
That is our reality. That is our reality. That is our firmament.
Well, actually, I think that isn't because the spoon, the fluid would have to match the velocity at the actual source. So the driving force would. So actually, the spoon would be the surface, and then the you would see that it would be slower as it would go out. But once again, that's because there's relative velocity between the two. But
Which
once
there isn't
again,
with the earth and the atmosphere.
yeah, and so there shouldn't
Which
be
is
any
why I said the
friction
cup
between the
would be
earth and
the
the
earth.
atmosphere. Yeah, that's what you'd think, but it technically it works both ways, and one of them is it's pedantic. It doesn't matter. It's not
Well,
important.
no, there's something moving the spoon is the problem, right? Like there's
Yeah, and
something that